This conference will now be recorded.
Yeah, hello everyone and welcome to day 2 webinar. Can we wait for a few more minutes so that all the speakers could join the webinar? Today
This
is
conference
Dr.
will now be recorded.
Digambara Patra from American University of Beirut, Lebanon. Hello, Dr. Digambara. Are you ready with your presentation?
Hello, good morning. Good morning to everybody, or good afternoon, maybe for many places. Yes, I'm ready. How can I share my presentation?
I gave you access to share your presentation. Please click on the share button and you can share your screen with us.
So I can share?
Yes, you will be getting a pop-up to share the screen.
Okay. It's not active, right?
No, I have given you the access.
Yeah, you have to give me access. Yes, please.
Yeah, I have given you the access. You are the presenter now.
Can you see now? Accessibility
In
included
the bottom of your
mouse.
screen, there will be 4 buttons. Click on the screen button.
Yeah, I click it and it's asking when you are done, restart to go meeting apply.
Restart.
Yes, can you see me again?
No, your screen
Accessibility
is not.
features include keyboard, mouse, control. Okay. Now does it work now?
No, it's not visible.
I gave the accessibility. I click it and because it is showing it's cross. It is not active, as if you have not given me permission.
No, I have given you the permission. Here it is showing that you are the presenter now. Please follow the instruction which it is showing. If it is asking to restart, can you please restart that? Go to Meetings app.
Okay. Again, it's the same thing.
Oh. Is it asking for any permission on your system?
I gave it. It is asking something like required password. I said no. And privacy setting, I put go meeting. Okay. Let us. Okay. Let me see whether it works now. Did it work?
Again, I have given you permission.
Yes. Screen. I gave you permission. Okay. Now, can you share it? Can I share it now?
Yes,
Can you
please
see?
try. Yes, yes. Now it's visible.
Yes. Okay. I think there was some problem with the software of the Go
Yes,
method.
yes.
Okay.
Okay, you can start your presentation.
Sorry for that disturbance. Shall I begin now?
Yes, you can begin.
Okay, good afternoon to everyone again. And today I will be sharing some of our experiment related to green chemistry and while preparing different kinds of metallic nanoparticles. But I will be focusing only on catalytic applications, although we work on different aspects like sensing applications. So first thing, when I begin with, let me introduce why I use this chemical or the compound which is very common and all of you may have used in life sometime to use spices like turmeric. So turmeric is one of the most popular compound used in food as a color, as a spices, as also a taste. In many places it is used as a food spices, and also it is used in curry. In Lebanon it is used in sweet. It has also many other applications, especially in medical applications. People are trying in pharmaceutical uh, applications for anti-cancer activity, and anti-inflammatory activity of curcumin is well known. Curcumin comes from the turmeric. It has a structure like this, and also it is used for like Alzheimer's disease. People are working on it. There are many different aspects. But in this work, I have used this as a reducing agent, a mild reducing agent, as a green chemistry tool. First thing, why I use this? First important thing is most of the biologicals or the system we use, sometimes we don't know the toxicity. Even we say this is plant extract and we say it is bio comfortable, or we can say it is environmentally friendly and it is green, but sometimes some of the plant itself can be toxic. So curcumin is well established. Even in clinically, you can use 8 gram per day, per day, and it is safe. So even if you are using in day-to-day life, so it is quite well known and well established as a safe compound. So this is why I use this compound in the lab to avoid other toxic chemicals and also toxic reagents. As we also use in one of the other part of our project, this molecule as a probe molecule, as a green probe molecule, to investigate various kind of biological systems like membrane, protein. So we investigate their properties in this case. So why green synthesis is very important? First, green synthesis is eco-friendly, and we want to have a recyclability. So we will have less amount of toxic reagents, and this is what it traditionally is the way.
Yeah, hello, Dr. Patro. I'm sorry for the interruption, but we cannot able to hear your presentation. Yeah, hello, Dr. Digambara.
Hello, can you hear me?
Yes, now we can able to hear you. Can you
Yeah.
please repeat the 2 slides as we cannot able to hear your presentation?
Okay, I will. I will. Sorry, I'm able to share it now. My slide. Can you
Yes,
see
the
it?
slide is visible.
But it's not moving. Sorry,
Yeah,
first time using Go meeting, so I never use it. We used to use Zoom.
okay. Okay, no
So this is
problem. I
why.
can guide you through the process.
Can you check it how I can share the file?
Yes, yes, just a
Something.
minute.
Yeah.
Yes, please share your screen with us again.
Yeah. I think the connection was
Yes, perfect.
Now,
Now it's visible. Now please start your presentation.
oh, I cannot see my. Uh, can you see the
You can
slide now?
close. Yes, yes, yes.
Yeah. Okay. I will repeat it again. I'm
Okay.
sorry again. I will try to maintain the time. Okay. Whatever I
Yes, no
lost.
problem. There is no problem about the time. It happens sometimes. It's an online webinar.
Okay, thank you. So green chemistry. So basically, green chemistry is eco-friendly, and we want to reduce the chemical toxic, and this is why we use different chemicals. And one of them, as I mentioned to you, we will be using the curcumin from the turmeric. So nanoparticles, when we talk about nanoparticles, basically we mean to nanomaterials which have a size in between 1 to 100 nanometer. As you know, mostly in chemistry, earlier days, we focus in the atomic scale or in a molecular scale to understand the bulk material. And one area which was never focused in when chemistry was developing is in this time scale when we prepare materials in the nano level 1 to 100 nanometer, or sometime it can go up to the 500 or 600 nanometer. Other objects what we know in the molecular scale like a DNA molecule or virus, bacteria, all these biological systems including our human hair, relatively it was well understood. We established that, and we also applied in our day-to-day life. But this small window, 1 nanometer to 100 nanometer, there was not much study because these particles are finally either they disintegrate and we go to the atomic level, and then we combine sometime, or they combine and form the bulk material, largely because these materials are not stabilized in this level, although there were few nanoparticles which were known in our day-to-day life, like a small aerosol or dust particles. Why this is important now? So last 30-40 years, again it was realized that if we tune the materials in this range 1 to 100 nanometer, the optical, thermal, electrical and other kind of properties dramatically changes compared to the bulk materials. So this is why the focus came in the nanomaterial level, and then we moved to prepare different kind of nanomaterials based on different kind of system. For example, we can prepare nanomaterials using organic system like carbon based nanoparticles. You can also prepare nanoparticles based on metals like metal, copper, nickel, gold, silver. Then also another kind of nanomaterials, which is basically not single molecule or not is a ensemble like micelle or lipid-based nanoparticles, where you use polymers along with the lipid or polymers. There are other brands like semiconductor nanoparticles, polymeric nanoparticles, ceramic nanoparticles. We can also prepare nanoparticles in a hybrid structure. We mix metal and metallic nanoparticle and polymer, let us say organic and inorganic materials. So today I will be just focusing on, although we have prepared nano hybrid particle also, but today since I will be only focusing on the curcumin as a reducing agent, I will just focus on the metallic nanoparticles. Why metallic nanoparticles also are more exciting? Because the size and shape of the nanoparticle itself can vary the property. Using the same chemical, we can get different kind of properties or activity, which was not known in bulk material earlier. Only we knew that effect of concentration. So now we will understand the size or shape of the nanoparticles, how it can influence the properties. And today I will be focusing on the catalytic properties. So sometime we can prepare these nanoparticles in just like a sphere, sometime like a wire, a long wire. Sometime long wire means the thin, the thickness is in nanometer scale, but the length can be in micrometer scale. It can go to few hundred nanometer to micrometer. Or we can also prepare nanorod. Nanorod has relatively smaller length, about 100 nanometer or 200 nanometer. We can also prepare nanoflowers and other nano grains and so on. So I will be sharing some of our results. So before that, one of the interesting properties about gold or silver nanoparticle is their surface Plasmon resonance property. When we use surface Plasmon resonance property, that means the metal nanoparticle absorbs, and in this case in the visible region, and this gives different color based on the size of the particle. That means we can vary the optical properties by changing the size of the nanoparticle. Here one example from 30 to 90 nanometer, but you can go to the smaller also, and you can go to the longer length, and even you can go for gold nanoparticle, you can get from the blue to the red region. Now, second aspect of the nanoparticle is how to stabilize it. So for stabilizing, as I mentioned earlier, if you take the metallic nanoparticles, they will combine. Even they prepare in the beginning, when you prepare the nanoparticle, you use a reducing agent, then maybe one atom will be reduced, and then it will form a metal structure. Then this may recombine, or they may combine themselves and prepare a larger particle. So our approach is to put something in between to stabilize the metallic nanoparticle in a given solvent and control the size. So for that, many kind of materials are used. So like proteins, liposome, these are some people have tried biological system. Also you can use other like polymers you can use, or like PEG you can use. Any kind of surface modification like surfactants are quite common, because surfactants help the metal nanoparticle to get solubilized in water. So this gives different size and different shape, and each nanoparticle, when we grow, they have different mechanism. You can grow like a small rod or a wire, or you can grow like in the three-dimensional structure to form a larger sphere. So in one of the first project, we use curcumin as a reducing agent to control the nano rods. So earlier report was known that ascorbic acid is used for this purpose. So in this case, what scientists or other people have worked is they use a seed mediated method. In this case, they take a given amount of gold nanoparticles which are already prepared, then use a mild reducing agent like ascorbic acid, and then they prepare gold nanorods like this kind. So first time we tested the curcumin one, and we tested different mechanism. We changed the different surfactants, like as you see here, we use surfactant CETAP, like cetyl trimethyl ammonium bromide. We also use like citrate, and we saw how the surfactant itself changes the selectivity towards the metallic nanorods. So in this case, gold nanorods. Like in this case, we have very high yield of gold nanorods when we are using CETAP, of course, along with the additional amount of gold salt, and silver ion also is used in this case. So on the other hand, if you have in case of if you use another condition and you use citrate, then nanorod yield is low. And in another case, we have only citrate and we don't have, let us say, curcumin. We have curcumin, of course. We can have nanorod, only nanoparticles. So this one we investigated, we published the mechanism also. Then we thought, why use a seed mediated nanoparticles for growth of nanorod? Because while preparing seed mediated nanoparticles, you also use sodium borohydride initially to prepare the gold nanoparticle. So we say, let us remove the step and let us start from the beginning. From the beginning, only gold salt and curcumin, and of course, we optimize different conditions. We use different surfactant. We use also silver ion. Without silver ion, we use different pH, different temperature. I will be just focusing only one part, one application when we prepare gold nano wires. So if we use, let us say, in this case, we use CETAP and silver nitrate along with the gold. We use the pH 13. Then we add curcumin and we reduce it. And this is for pH 13, but we applied for all the pH 4 to 13. And what we will see, as you see here, when we get pH 4 to 11, we get spherical gold nanoparticles. But as soon as we go to pH 13, we get nanowaves, a long thin nanowave. So this was quite interesting for us, and then we characterize them. Of course, as you see, all of them have gold, whether pH 7 or 13. We had for other just X-ray diffraction pattern. So here are the shape for different pH 4, 7, you can say 9, 11. Then this is the pH 13. Then what we did, okay, of course we characterize. I'm not going in detail, but why we will go to the catalytic activities. So we tested these particles for the reduction reaction, where we use para-nitrophenol to make it para-aminophenol, and this is a well-established reaction, and sodium borohydrate is used for reducing it from this one to this one. And we cannot use like a curcumin agent because these are the weak reducing agent. So in this case, this is the traditional reaction where we use gold nanoparticle, and gold nanoparticle is used as a catalyst. Now we did the same thing. Of course, it is known in literature also, gold nanoparticle was used. Then we monitor using the UV visible spectrophotometer. So basically we monitor the absorption spectrum of para-nitrophenol as well as para-aminophenol. So this side, during the catalytic process or reduction reaction, the absorbance decreases, this increases for the para-aminophenol. Then we compare the rate. Of course, we did, as you see, for different. So first, when this is for the case for different concentration of gold nanowaves. So as you see, gold nanowaves effectively reduce it, and this is for different concentration. As the concentration increases, then your rate of the reaction also increases, and this is what we got. Now if I go to different pH, as you see, pH condition means we go from the gold nanoparticles which are spherical to the wire, and what we found, the wire has very high activity compared to particles. Almost, as you see, the 4 times the rate constant is 4 times that of preparing at 4. So rate was almost 10 times if you overall, if you see the speed of the reaction. So this is where we found that by just changing the shape of the particles, you can enhance the catalytic activity. So then we also use another synthetic procedure. Then we said in previous case we use surfactant. As you see, we use CETA, we use the aqueous medium. Then we tried something, let us not do anything, just we add curcumin and silver salt to prepare in a solid state green synthetic approach. So here we take silver salt, silver nitrate, we add curcumin, we grind it. So after grinding, when the color changes, then we wash with the ethanol. As you know, ethanol can be easily evaporated. So then we, of course, we wash it. Then with the ethanol, we remove the unreacted. As you know, ethanol is also a green solvent. So we remove ethanol, and then we characterize the sample. And as you see here, the X-ray diffraction pattern of silver nanoparticle. We also do EDX and SEM, we characterize it, and this is one of them which shows as we increase, this is the time scale kinetics for different time from 1 hour to 7 days we did, and we see the growth of the nanoparticle. What was interesting is as we keep the rate or as we keep longer time, what we found the fluorescence intensity increases. That means we have a higher conjugation of curcumin. This is something very interesting. That means the particle also changes, particle size also changes, as well as the concentration of curcumin attached to the or conjugated to the silver increases. So then we did the same way, we did the para-nitrophenol reduction reaction, and here also we found the size plays an important role. In this case, no shape, only which vary the size. And what we found, the smaller nanoparticle has higher catalytic activity in case of silver nanoparticles. The smaller size has more efficient, and what we found is the larger size reduce the catalytic activity. Of course, we get the kinetics, thermodynamics parameters. I'm not discussing then here how the mechanism is, how paranitrophenol is reduced to 4-aminophenol. Then we were excited, we did from zinc oxide, but I will not discuss because zinc oxide is not reduced. Basically, there it is conjugated. Zinc oxide, in zinc oxide, curcumin gets conjugated rather than it is reduced to completely zinc metal. It is not possible, as you know, zinc oxide. So there also we found different application for degradation and adsorption study and sensing application. Here I will show you about the copper oxide nanoparticle. As you know, copper oxide nanoparticles are cheaper than silver or gold, and it's more practical to use. So we use a modified conditions, and we use copper chloride. Of course, we tried different kinds of copper salt. So cuprous also we tried. So cupric and cuprous both we tried, and then we may prepare the copper nanoparticle. One thing is very difficult to distinguish whether it is copper oxide or copper nanoparticle. And in literature, it's very difficult to confirm, and we also could not confirm because their XRD patterns are very similar. So we prepare in different conditions by changing the pH and changing the temperature, and we prepare two different shape of the copper oxide nanoparticle. Like as you see, one is the grain kind, another is spherical kind, and this is the EDX. It's then as you see, copper oxide powder, then copper oxide without CTAP, copper oxide with CTAP using a conjugating reagent. Then this is that of the curcumin, and this is CTAP. So as you can see, in all cases we get the peak of copper or copper oxide nanoparticle. Then also we establish using FTIR their interaction for the copper oxide nanoparticles. So I'll skip it just for characterization. These are. So then there is something again. We tested it for reduction reaction. So here we reduction of, like here, as you see here, this one gives us how much of curcumin is conjugated. As you know, CTAP, this is the TGA data. I did not show for others, just to establish how much of organic materials we have in with CTAP and without CTAP. As you see, in without CTAP, we have very less amount, which is because of the curcumin only. So then we apply this one for methylene blue, one of the most popular dye is used, and it's one of the great environmental pollutants because this is used in many industry, including textile. So there are many different ways to overcome this for degradation of this dye in water, especially when it is released after dyeing purpose. Then silver and gold was known particles. These were used in science or in research. So we tested for copper oxide nanoparticles. So we do the similar now in the presence of sodium borohydrate. We did the reduction reaction. Then we use copper oxide as a catalyst, and we compare it. As you see, this is without any catalyst, this is with catalyst, and we compare the nanoparticles, spherical one and nano grain one. And you can see here, nano grain has higher catalytic activity compared to your copper oxide nanoparticle, the smaller spherical nanoparticle or the size, the shape. So this is what was my conclusion is, if you twin the nanoparticles, then of course you can vary the catalytic activity. So using the same nanomaterials, of course, we have planned to use for nano waste like copper oxide and different kind of shape as nanoparticles, and compare between the different kind of nanoparticles. In our other project, we also work tuning this nano size or nano shape for changing the optical properties. Especially we work on resonance rel scattering. The scattering phenomena, like we found in one of our cases, nanowire is higher optical properties than the nano particles, the spherical one. That means we can increase the sensitivity when we are devising a sensing scheme, or also we can also sometimes use for enhancing selectivity. Okay, this is Beirut. So you may have heard about the explosion last year. So something happened around this region, and our university is somewhere here. This is our university. It has a beautiful campus. A few years ago, it was one of the 10 most beautiful in one of the rating 10 most beautiful university campus in the world. So, and this is one of the popular place. Thank you very much. If you have any questions, I can take.
Thank you, Dr. Digambara, for your presentation. Is anyone having any questions?
Please help me how to remove this one for others.
Yes, it's removed. Okay, he left the session. So we can move toward the next presentation, as our next presenter is Dr. Muhammad Asim, but he has not yet joined. So I would request Dr. Mirela Shukweva from Hellenic Mediterranean University, Greece, to present her speech. Are you ready with your presentation, Dr. Mirela?
Yes, let's say so.
Okay.
I'm never ready with a presentation. I always have the tendency of changing it. So
okay. So I have given you the permission to share your screen.
Is it visible?
Yes, it's visible. Yes.
Okay.
You can start your presentation.
I'm losing my connection. Okay, it's fine. Thank you. That is not.
Okay.
I do have some things. How do I get rid of them?
Yes.
No.
Please start your explanation.
Yes, of course, but my slideshow is not visible in my screen. I have some. I guess you can see it. I have some windows left, and I suppose they are also on share. So
no, they will be not visible to us. It's for you only. You can leave it
so
like
you don't
that.
see them. I thought that once I shared, it might be visible for everybody, and it's really disturbing.
No, we can only able to see your presentation only.
Okay. So I'm going to present you some of our work regarding composite nanofibers for improved photocatalytic performance under UV and visible irradiation. As you may already know, there are a lot of problems regarding. Excuse me one moment to close the door. I'm in the lab and someone left it on.
Okay.
And it's making bad noise. So I'm back. Concerns regarding environmental protection issues like water pollution and air pollution. So our work is focused on engineering materials designed for water and air purification application using photocatalysis. Most photocatalysis based applications today are using titanium dioxide. We do the same, but we try to solve some of the problems of the present titanium dioxide nanoparticles that are commercially available and used in water purification application. One of the most difficult issues to solve is keeping the photocatalytic activity while nano size is not exactly nano, because the new rules regarding use of titanium dioxide, I don't know if everyone heard of it, but there are new regulations that titanium dioxide was included on non-desired nanomaterials. So for the moment, it's forbidden in using for cosmetics and food applications, but it seems that it will expand its ban. So we are trying to overcome this problem by making titanium dioxide nanostructured but trapped in a larger material, let's say, like fibers or membranes or mats or so. Our studies are targeting fabrication of titanium dioxide with narrowed band gap in order to expand its use from UV region of the electromagnetic spectrum where it usually works due to its native band gap, which is about 3.2, 3.24 actually electron volts. To reduce the band gap in order to make it usable also in the visible spectral region. And we actually did succeed quite well. So I'm moving forward on showing you some of our materials. In order to achieve the goal of fabricating nano titanium dioxide based materials in a trapped form, we use electrospinning. Electrospinning combined with calcination. Electrospinning, it's a very easy and quite cheap technique that permit also the scale up in an easy way. What you see in this slide, it's a schematic of our electrospinning setup. The usual electrospinning setup consists on a syringe, a needle, and a collectory rotary disc metallic. Between them, it's applied a high voltage. So we use normally a flow rate of 75 milliliters per hour for the precursor solution to be injected in the high electric field through this needle, which has 0.8 millimeters diameter hole, and the resulting material is collected on this disc. What we get out of this process are such kind of fibers. So varying the growth parameters and the properties of precursor solution, we can obtain a variety of fibers with different diameter, length, and physical properties. These fibers are calcinated at various temperature according to the material. I speak in general for the moment. And we get resulting fiber-like, ribbons-like structures, three-dimensional structures that are formed from nanoparticulate oxide semiconductor materials. So I'm going to show you some of our materials based on titanium dioxide doped with silver, copper, and lanthan today, but we are working on a large variety of dopants, and we achieved to cover almost all electromagnetic spectrum in visible region for activity. So the materials I mentioned before, we prepared following this, what you see, these conditions. The precursor solutions are mentioned here, but I will not read or explain all those details because I don't think that someone will remember them. So if you wish to have you just ask the presentation, I can provide to anyone without any problems. So following the idea of electrospinning growth of such materials, I'm showing you here some of our copper doped titanium dioxide, which we get at first on the form of fibers with diameter ranging from 60 nanometers up to 210, but the medium value is somewhere about 120 nanometers diameter. After calcination, we obtain nano-structured ribbons with quite good stoichiometry. I don't know if you can, actually you can see the X estimation of the concentration of various elements in the material. So it's quite stoichiometric. And in the lower images, you can see the nanostructuring of these wires in some transmission electron microscopy images. For sample with 0.1 atomic percent copper. In the left side, I have included a mapping image of a wire that looks so strange because the holder of the electron microscope had copper also in its structure, and we try to isolate the effect of the background copper in order to see if our fibers have a uniform distribution of the dopant in their structure. So you can see the mapping for titan, oxygen, and copper in the red in the lower image on the black background. And the large image is the superposition of the three elements mapping on this specific sample. Moving to silver doped titanium dioxide, we get more or less the same kind of three-dimensional ribbon-like nanostructured fibers, ribbons with various diameters. But their diameter it's actually varying very strongly with the dopant concentration, as you can see in these scanning electron microscopy images. As the dopant concentration increases, the medium diameter of the fibers decreases. In the same way, we can tune size varying the temperature for calcination for a specific formulation. I have also included some scanning electron microscopy images of pure titanium dioxide that we obtained by this technique, as well as lanthan doped titanium dioxide samples. In the, can you see my mouse moving, or when I show something? No feedback. Am I still online? Thank you, Alexandra. So I included also a couple of images of transmission electron microscopy obtained by transmission electron microscopy in dark field and white field in order to show the nanostructuring of those materials. You see them here. This is a very high magnification, very high, 300,000 times magnification on the end of this specific fiber copper doped titanium dioxide. lanthan doped titanium dioxide sample. So very well and nice structured. Of course, we use X-ray diffraction analysis in order to screen the crystallinity of our samples. We can tune crystallinity and material phase by tuning the temperature for calcination, and we can obtain from a combination of all the three titanium dioxide phases, or only one of those phases, rutile and anatase, according to the growth procedure. You can see in the upper part of my slide the variation, X-ray diffraction spectral variation with the calcination temperature from 400 to 700 Celsius degrees for titanium dioxide doped with copper. And you can see that at low temperature we get a combination of anatase and rutile. At about at 700, the most dominant phase become rutile, and in the medium temperatures we have the most presence of anatase. In the other slide, you can see the variation of X-ray diffraction spectra with the concentration of the dopant. And this is an image for anatase phase titanium dioxide. It's the one growth at 400 Celsius degrees, which has the most strong signal for the anatase presence in the material. The same kind of spectra I included for lanthanum doped titanium dioxide in order to see that we really can obtain the desired crystallinity for our material by tuning temperature and dopant concentration, and achieve the desired physical-chemical properties. It's also an X-ray diffraction showing the variation of X-ray diffraction spectra with the concentration in the case of silver doping the titanium dioxide. So we prefer the anatase phase of titanium dioxide because these seem to have the highest photocatalytic activity, but we are using also the other possibilities for various other applications. We monitor all the time our the optical properties of our materials. You can see here tau plots. Okay, the absorbance plots and tau approximation for getting to learn the band gap of our materials. And as you can see in the case of copper doping, we can tune the band gap from 2.65, actually 2.64 electron volts up to 2.71. With silver, we can achieve band gaps of about 2.4 electron volts, while using lanthan, we move from 322 down to 20.60 again. So we can obtain materials that works also very well in the visible region of the spectrum. photocatalytic activity, we are measuring using UV reactor of type special, German company providing such kind of tools. So it's a standard equipment that allow us to control and keep constant the temperature. During the measurement, the solution is continuously stirred, and we really can have the certain certitude of having constant thermodynamic parameters during the measurement. The same way in measuring in the visible region of the spectrum, we use a reactor that it's custom made using a visible spectrum lamp of 400 watts power, which is placed at 15 centimeters distance from the reactor, that is also having a cooling system that permit temperature control. Our measurements are done at 20 Celsius degrees. And in this case, in the case of measurements that you see here, the photocatalyst quantity that we used was 1.66 gram per liter. But this is one of the many possibilities that we usually try. I will show you later on a slide on optimization of photocatalyst quantity for a specific measurement. So we monitor amaranth dye decomposition in the presence of our material. Amaranth dye was used on concentration of 25 milligrams per liter, and the irradiation time was 240 minutes, but we go sometime at 300 minutes in order to make sure that we have the whole recorded the whole information. As you can see in the graphs, the absorbance spectrum was measured periodically, and we can see the decomposition, almost a complete decomposition after few hours, not the whole 6. I think the yellow mustard is already almost gone. Yeah. The first measurement showed the pure titanium dioxide activity. The second spectrum regards image regards the copper doped most crystalline and most suitable for this process doped sample. So we have sorry. You can see actually for each copper concentration how the composition efficiency is in the left right corner down of my slide. I cannot see it, that I have some windows I cannot really move from here. Okay, I can. Stop. I think something is wrong. I cannot change slide.
Maybe you can try to share it one more time and it will work.
Okay, I'm going to try again.
Okay,
Let's
can I
see.
know what's the problem? I'm sorry.
I cannot change slide. I cannot move it. Looks like frozen. I mean, I
Okay,
cannot.
once press
Okay,
the escape
it's
button.
okay.
Yes, yes.
It's okay. It's fixed.
Okay.
But for a moment, it was frozen and I couldn't do anything. Okay.
Okay.
Here are some decomposition kinetic curves for so the concentration decay in time for titan dioxide pure titan dioxide samples and the copper doped samples, as you can see, and also I have included kinetics for the lantern doped. Sorry. Those are under visible light, so we have 99% decomposition of amaranthine in less than 2 hours. And in the right side, you can see, as I promised, the effect of changing the photocatalyst concentration in the solution. So you can see that 4.2 grams photocatalyst, 4.2 grams per liter photocatalyst, it's let's say slower the process of decomposition than for larger quantities, but there is not a significant difference in between. So we succeeded to have photocatalytic activity again. In visible region of the spectrum, and actually again I cannot change slide, sorry.
Oh, you can press the escape button. Please press the escape button.
It's happening nothing. I
You
did
go
also that.
like you are in the full screen mode. Go back to normal mode first.
I would like to do that if it will respond to any. Doesn't work, sorry.
Or you can double click the
Reshare.
mouse.
I will reshare. It's not answering to any commands. That's the problem.
No,
Nothing.
first you double click the mouse on the screen itself.
Okay. I think we are to the next slide. Yes, here you can see also some decomposition spectra on pure titan dioxide and silver doped titan dioxide against methylene blue, with again efficiency of over 90%. And in the lower part of my slide, there are the decomposition decay, concentration decay for various dyes tested on silver doped titan dioxide. As you can see, methylene blue, Congo red, amaranthine, and orange too were tried also, and the best fastest decomposition we saw for Congo red, followed by methylene blue and amaranth and orange. The constants, the composition constants are in the table. I move faster because I think I lost a lot of time on blocked slides and explaining structure. Again, methylene blue decomposition using lanthanum doped titan dioxide, and the effect of temperature for the same dopant concentration. The temperature of annealing on pseudo first order calculated constant, kinetic constant for lanthanum doped titan dioxide. Kinetics against methylene blue again. And again, the effect of catalyst dose, you can see that using different quantities of lanthanum doped titan dioxide photocatalyst from 0.2 grams to 1 gram, we actually get concentration decay on the same range from at a higher catalyst concentration. Okay, it happens faster, but the difference is not huge. The best of those materials will be integrated in membranes that will go to real life applications. Again, no, okay, it worked. And here I have included also image regarding photocatalytic activity of 1% lanthanum doped titan dioxide nanofibers against ciprofloxacin antibiotic, which is one of the most used recently, and it's found in many water surfaces, wastewaters from home appliances. It has it's a big problem for the water cleaning plants because it quite destroy the bacteria that are doing the fermentation on the wastewater cleaning beds, and that's why it's of our interest among others. So lanthanum doped titan dioxide proved to decompose ciprofloxacin in quite large concentration. We use the same 25 milligrams per liter, which is much more than you find usually in the wastewaters, and it has a very good decomposition rate. You can see that in 100, almost 200 minutes, it's completely removed from the waters. And this is active also on visible region of the spectrum. Regarding the reuse of those materials, we remeasured and rechecked them after a number of uses, and we found out that they keep quite well their physical properties and also the color removal efficiency. You can see in this slide that it changed from 99.84 to 99.1 after 5 cycles of use. Here it's the same characterization for lanthanum doped titan dioxide reused. So this one is losing part of its efficiency, and but still usable and doing the job after some cycling. If I remember well, yeah, 5 cycles in the second round was this. Sorry, so this was done actually 10 times. Here I show you also another application, the antibacterial activity of silver doped titan dioxide against Staphylococcus aureus and E. coli. This is one of the simplest tests that are performed in order to establish if a material has antibacterial activity or not. So it's the agar plate culture, and you can see that we got quite good inhibition zones for Staphylococcus aureus 16 millimeters and 19 millimeters for E. coli, for the sample with the highest silver concentration, and a bit lower for the samples with lower from 1% silver atomic silver concentration in the material. So the conclusions are that using this technique we can achieve quite efficient nanocomposite photocatalytic fibrous materials. We can control the properties of the obtained material by controlling the temperature to achieve the desired crystallinity as well as the diameter size of the fibers. We can do this using a technique that is suitable for scale up. These materials reduce the risk of environmental contamination with nanomaterials themselves, and they are easy to recover and rejuvenate and reuse. They are suitable as well for other applications such as health or electronic and optoelectronic materials with those properties. Thank you very, very much for your attention, for the invitation to this webinar, and please ask me questions if
Thank you,
you
Dr.
would like.
Mirella, for your presentation. Is anyone having any questions?
Yes, I have one.
Please.
Hello, my name is Aleksandra Kędzierska-Sar from Poland, Łódź University of Technology. You use 3 dopants, silver, lanthanum, and copper, yes?
Yes, this is what I show today, but we are using also other metals in this in the same kind of process.
Okay, so which of those dopants were the most the best, like gives the best results of catalytic process, or it is
actually among those we have various formulations that has the best in a specific range of
application?
wavelength.
Okay.
Yeah, so and they are more active in a specific region of the spectrum. The idea is that using a mix of these, we can achieve a kind of composite material in a membrane, embed various fibers like this in a membrane, and we have activity on all solar visible
Okay, different energies and then different applications.
Yes.
Okay.
That's the idea. So
okay, I understand. So I will be very grateful if you could send me your presentation if it's not a problem, or some link for publications.
that will be my pleasure.
Okay.
I will ask the organizer if it's possible to put us in contact.
Okay, I can send you my email just by message here.
Perfect.
Thank you very much.
You are welcome.
Thank you, Dr. Mirella. Is anyone having any else questions? Okay, no questions. Dr. Mirella, you can share your mail ID in the chat box itself. You can chat with anyone you like if anyone is interested to share your contact address or to take contact, you can initiate a chat in the chat box.
Yes, thank you.
Okay, so for moving on to next presenter, actually Dr. Khalida Naseem requested us to present his speech now as she is having some emergency work. So hello Dr. Khalida, are you ready with your presentation? I'm sorry we cannot able to hear you. Hello Dr. Khalida. We cannot able to hear you. Yes, your presentation is visible to us, but your voice is not audible to us. We cannot able to listen you.
Maybe you need to remove
Yes.
Mirella, Dr. Mirella from presentation, and then
No,
Dr.
she's
Khalida.
not. Yeah, Dr. Khalida is now the presenter. We can able to see her presentation as well, but I think there is a problem with the mic or speaker she connected with the system, I think.
Okay.
Yes. Hello, Dr. Khalida. Can you please change the speaker you connected or headphones you connected to your system? Hello, Dr. Khalida. Can we take a lunch break till then so that you can check with your issue? Okay. Thank you for acceptance. So we will take our lunch break now, and we'll be back at, sorry, it's 14 o'clock. It will be a half an hour break, and please stay connected with us.
Hello, can anybody listen me?
Yeah,
Are you
hello, Dr.
listening?
Khalida. Yes, yes,
Okay, thank you so much.
yes.
Thank you.
Okay, then after the break, I will be making you the presenter. You can give your
Okay,
presentation.
okay, thank you so much.
Okay. Yes, hello everyone. Thank you for staying connected with us. So we will start our sessions. So now Dr. Khalida Naseem will be presenting her speech. So
Yeah, I am here.
okay, so I'm going to make you the presenter. Just a minute. Yes, you are the presenter now. Please share your screen with us. Yes, it's visible. You can start your presentation.
It's not visible in full screen.
You can like click on the last button at the bottom of your screen. Yes, that one. Yes.
Okay, thank you so much. Here is Dr. Khalida Naseem from University of Central Punjab, Lahore, Pakistan. And here I will present one of my project that is about the preparation of core shell hybrid microgel particles and their application as a catalyst. How I can shift to the next slide. I'm unable to
Yes, you can click on the
shift to the
mouse.
next. Okay, thank you. So as we know well, metal nanoparticles are actually small particles, and they aggregate rapidly to form the bulk material. And when their size is increased, their catalytic properties are mostly lost. So actually, catalytic properties of nanoparticles depend upon their size as well as their shape. As the size decrease, their properties increase, because we know well that catalysis is the surface phenomena. And in literature, different nanoparticles like copper, cobalt, nickel, palladium, platinum, and silver nanoparticle has been reported. But in my research work, I prepared silver nanoparticles because we know the preparation of silver nanoparticle is financially feasible process as compared to palladium or platinum nanoparticle. But there is a problem with but there is a problem with a metal nanoparticle that they aggregate rapidly and they convert into the bulk material, and their catalytic properties are affected. So we need to take some sort of supporting material that can stabilize the metal nanoparticles for a long time and increase their recyclability. So different inorganic materials like zeolite, mesoporous silica, seashell, and different organic materials like graphene oxide and different other materials like biological materials like glucose and different gums and different plant extracts can also be used as a supporting material, because the functional group present in these biological materials act as a caging effect and stabilize the nanoparticles for a long time. Different polymeric materials like chitosan sheets, polyaniline shells, and microgel can also be used as a supporting material, but there are few drawbacks with the use of these material as a supporting material. So here we preferably prepared microgel particles as a supporting material to prepare silver nanoparticles and to stabilize them and to prolong their lifespan. And what was the reason? Reason is that microgel particles are actually the colloidal gel particles, and they consist of cross-links three-dimensional polymer network. And the size and the sieve size of the microgel particles can be tuned by changing the external parameters like pH, temperature, ionic strength, and different other reaction conditions. So just by changing the external condition, we can tune the sieve size of the microgel network, and as a result we can also tune the size of the nanoparticle. This was the actual purpose why we choose the microgel as a supporting material. And depending upon the composition of a microgel, different functional groups are present, and those functional groups actually act as a caging effect or act as a cage to stabilize that nanoparticle. So as compared to previously reported different type of supporting material, microgel act as an efficient supporter to stabilize the nanoparticle. When we incorporate some non-polymeric material with microgel, then the resultant microgels are called hybrid microgels, and these microgels maintain the properties of pure microgel and that of the metal nanoparticle, like high catalytic activity and external parameter like sensitivity to pH and temperature. So we can use synergistically both the properties of both components like microgel and nanoparticles. So this was the actual reason why we chose this system. Hybrid microgel can be classified into different groups depending upon their morphology, like hollow microsphere. In these microgel, nanoparticles are fabricated in outside shell region. And the second one is core shell microgel particles, in which central metal nanoparticle core is actually prepared, and then microgel shell is constructed around that core. In the third one, homogeneous microgel particles are prepared, and then these particles are covered with metal nano rods or metal nanoparticles. Fourth one is homogeneous hybrid microgel particles, in which metal nanoparticles are equally distributed inside the network. And the last one is core shell hybrid microgel particles, in which core is made of one type of polymer and shell is made of another type of polymer, and the metal nanoparticles are incorporated inside the shell region. Here we actually first prepared the homogeneous hybrid microgel particle, and then we prepared the core shell hybrid microgel particle to overcome the problem which we faced during the use of homogeneous hybrid microgel particle as a catalyst. So what drawbacks we face during the use of homogeneous hybrid microgel particles as a catalyst during the catalytic degradation of a toxic pollutant? First problem was its recyclability. Homogeneous hybrid microgel particle cannot be recycled easily from reaction mixture. And the second drawback of this system was that the reactant actually during catalytic reaction diffuse into the microgel network and approach the surface of nanoparticles. So in homogeneous system, reactant faced much diffusion barrier, and as a result their activity was decreased to a large extent. So to overcome this problem, we prepared core shell microgel particles, in which central core was made from one type of polymer and the shell was made up of another type of polymer, and nanoparticle was just restricted in outer shell region. So central core incorporation of central core increase the recyclability of the system from the reaction mixture, and the presence of nanoparticle in shell region increase the catalytic activity, as nanoparticle are just restricted in shell region, so reactant can easily diffuse into the microgel shell and induce high activity. This system induce high activity for the conversion of reactant into product. In our previous work, we used an isopropyl acrylamide based microgels, but these systems show volume phase transition temperature around 32 degree and they have dense sieve. So this system can just be applied up to 32 degree temperature, and due to dense sieve they show less activity and offer large diffusion barrier to the reactants. But in this study we use an isopropyl methacrylamide instead of an isopropyl acrylamide based microgel, and these microgel show volume phase transition temperature around 44 degrees. So this system can be applied at high temperature up to 44 degree, and further volume phase transition temperature was increased just by incorporating acrylic acid. And due to presence of extra methyl group, it induced the wide sieves, so less diffusion barrier was faced in this case. So which strategy we actually adopt to prepare our catalyst? In first step, we prepare polystyrene core. In first step, we prepared polystyrene core. For this purpose, we take calculated amount of styrene, napalm, and SDS. SDS was used as a surfactant or to control the size of particle. With water, stirring was done under nitrogen supply and heating at 80 degree. Ammonium persulfate was used as an initiator. Reaction was carried out for 7 hours, and dialysis was done to purify the polystyrene core. In next step, this polystyrene core was used as a seed to incorporate poly and isopropyl methacrylamide acrylic acid shell around that seed. And for this purpose, calculated amount of polystyrene core, napalm, acrylic acid, bis that was used as a cross-linker, and SDS that was used as a surfactant were taken in 3 neck round bottom flask. Stirring was done under nitrogen supply and heating at 70 degree. And ammonium persulfate was used as an initiator. Reaction was carried out for 4 hours and dialysis was done to purify the sample. In this way, we prepared core shell hybrid, core shell microgel particle. And next step, we use this core shell microgel particle as a micro reactor to fabricate the silver nanoparticle. For this purpose, microgel particles along with water and silver nitrate were mixed under nitrogen supply for 30 minutes, and then sodium borohydride was added to prepare the silver nanoparticle from silver ions. And after that, reaction was carried out for 1 hour, and after that, dialysis was done to purify the sample. Here is the diagrammatic representation of our work. In first step, styrene was used as a main monomer along with napalm, SDS, and APS, and polystyrene was prepared in first step. In second step, polystyrene core was treated with given reactants, and polystyrene p-napalm core shell microgel was prepared as shown here. And in third step, we treated this core shell system with silver nitrate and sodium borohydride and prepared core shell hybrid microgel system in which nanoparticles were just restricted in the shell region. This was the actual purpose of this study. Different analytical technique like UV visible spectroscopy, FTIR, XRD, DLS, and TGA-TEM was done to characterize the polystyrene core, core shell microgel, and core shell hybrid microgel system along with the monitoring of the catalytic reaction. To check either the nanoparticle are successfully prepared or not, for this purpose we scan the UV visible spectra of the prepared sample. As shown here, we can see that a peak was appear at 420 nanometer in case of hybrid microgel, but no peak was seen in case of pure microgel. This shows that nanoparticles were successfully fabricated inside the microgel network, and the change in color or change in dispersion color also shows the successful preparation of nanoparticles. We also study the pH sensitivity of our system, and for this purpose, the pH of the hybrid microgel particles was changed from 1.57 to 10.3, and UV visible spectra were scanned, and it can be seen from this graph that lambda SPR of nanoparticle was shifted to high wavelength. This shows that our system is pH sensitive, and it can be used as a pH sensor in future. And this was actually due to incorporated acrylic acid moiety that has carboxylic acid group. As we change or increase the pH, the carboxylic acid groups actually change into carboxylate ions, and that carboxylate ions induce the wide sieve size in the microgel network. So by just controlling the pH of the system, we can control the properties of the incorporated nanoparticles and microgel network. pH-based sensitivity or pH-based stability of nanoparticle was also monitored, and for this purpose, hybrid microgel system was kept at 9.3 pH and 2.38 pH for 18 hours, and it can be seen that SPR band of silver nanoparticle was not changed in the case of high pH, that was 9.3. But at pH 2.38, SPR band was appeared at 410 nanometer, but after passage of 18 hours, this peak was disappeared. This shows that our system was highly stable at high pH or in basic medium. Time-based stability was also checked, and for this purpose, again, UV spectra were scanned of freshly prepared catalyst and after 2 months old catalyst, and it was seen that no change in SPR band was observed. This indicates that our prepared catalyst is active and it is stable for a long time. DLS analysis was done to check the pH sensitivity as well as particle size distribution of the hybrid microgel particle. It can be seen in this figure that polystyrene core show non-responsive behavior to change of pH. But in case of core shell microgel, the hydrodynamic diameter of microgel particle was increased with increase of pH of the media, but after the increase of pH above than 8.34, the hydrodynamic diameter was decreased. This actually indicate the incorporated carboxylic acid group, which were changed into carboxylate ion with the change of pH of the medium. So carboxylate ions repel each other due to similar charge, and it induce the wide sieve size. Also, carboxylate groups are hydrophilic in nature. They attract large amount of water, and as a result, particle sieve size further increase. But the decrease in particle size after increase of pH above than 8.34 indicate that this was due to incorporated sodium ions screening effect. Actually, we use sodium hydroxide to increase the pH, so this decrease was due to incorporated sodium ions. But in case of a core shell hybrid microgel particle, it can be seen that particle size was large at the start, then it was decreased and further increased. Actually, at very low pH or in acidic media, microgel particles were aggregate and induce the increase in particle size. But as we increase the pH, aggregation level was decreased, and further increase of pH induced the partial and then full deprotonation of carboxylic acid groups. So this behavior indicate that our system show reversible behavior. We can swell it or we can deswell it just by changing the pH of a medium, and alternatively we can tune the catalytic properties of incorporated nanoparticles. TEM analysis was also done, and TEM analysis was done to find the particle size and morphology, and this analysis indicate the successful preparation of core shell type system. So by TEM analysis, the size of polystyrene core was found as 100.26 nanometer, and in case of core shell microgel particle, the size was 112.5 nanometer, and the shell thickness was just 12.3 nanometer. That was actually our requirement just to increase the catalytic activity of previous system as compared to of this system as compared to previous one, and the nanoparticle size was found in range of 9 to 12 nanometer. So the activity of catalyst was monitored just by checking the catalytic reduction of Congo red, and for this purpose we took calculated amount of Congo red sodium borohydride that was used as a reducing agent and catalyst in cuvette, and UV spectra were scanned in range of 400 to 650 nanometer. It can be seen here that absorbance of Congo red at 500 nanometer was decreased with time, and reaction was completed just in 540 second. This show high efficiency and high catalytic activity of our reported system, and the change in color also another indication of conversion or reduction of Congo red. At the same time, we also carry out the catalytic reduction reaction in absence of catalyst to check either the decrease in absorbance was due to the sodium borohydride. It was seen that there was a small decrease in absorbance value in absence of catalyst. So this data elaborate that the reduction of Congo red is although thermodynamically feasible process, but it is kinetically unfeasible. So we need to T10 minus 2 seconds. So the reaction was efficiently completed in the feasible time in presence of catalyst. And to find the value of apparent rate constant, we use this region at start. This region show the induction period in which although we have the catalyst and the reactants in reaction mixture, but it may be due to the presence of some oxygen over the surface of catalyst. So catalyst takes some time to be active. We just calculate the value of apparent rate constant from this region. And we also perform the catalytic reaction in presence of 10-month-old catalyst to check either the activity of our catalyst is maintained, its lifespan is long or not. So it was seen that in case of fresh catalyst, in case of reaction carried out in presence of fresh catalyst, the value of apparent rate constant was 0.63 10 minus 2, and in presence of 10 months old catalyst, its value was 0.61 per second. So this indicate that our reported catalyst was active with maintained catalytic activity even after 10 months of its preparation. Reaction was also performed in presence of different amount of catalyst that was vary from 0.146 to 0.390, and it can be seen from this graph that value of apparent rate constant was increased with increase of amount of catalyst. This indicate that as we increase the catalyst in reaction mixture, we actually are going to increase the active site in that reaction mixture. So more reactant will be absorbed over the surface of the catalyst and result in high value of apparent rate constant. To check either which type of mechanism reaction is going to adopt, we perform the same reaction in presence of different amount of sodium borohydride that was used as a reducing agent. For this purpose, calculated amount of Congo red and catalyst was taken, and the concentration of sodium borohydride was changed, and it was seen that with increase of sodium borohydride concentration, the value of apparent rate constant was first increased and then was decreased. So this trend actually indicate that the reaction follow the Langmuir-Hinshelwood mechanism. And again, reaction was also carried out in presence of different amount of Congo red, but same amount of sodium borohydride and catalyst, and graph was plotted between concentration of Congo red and value of apparent rate constant. And same trend was observed in case of effect of concentration of Congo red. So in case of Congo red, the concentration at which maximum value of apparent rate constant was obtained was 0.038 millimolar. So this trend also indicate that the reaction adopt the Langmuir-Hinshelwood mechanism. Recyclability of catalyst was also checked, and for this purpose we perform the catalytic reaction up to 4 cycles using the same catalyst, just recycling by centrifugation, and it was seen that percentage activity of catalyst was almost maintained up to 4th cycle as compared to previously reported catalyst that was homogeneous, a hybrid microgel catalyst which cannot be recycled easily from reaction mixture, but this core shell hybrid system can be easily recycled, and its activity was maintained just due to presence of a central polystyrene core. Different other dyes like methylene blue, brilliant blue, rhodamine B, and simultaneous reduction of a mixture of dyes was also performed, and it was seen that methylene blue was just reduced in 6 minutes with value of apparent rate constant as 0.625. Brilliant blue in 5 minutes with 0.484, rhodamine B in 25 minutes with 0.394, and it was seen that in case of mixture of dyes, the reaction was completed in 38 minutes. It shows that our catalyst is even efficient to reduce or to increase the rate of reaction if we have multiple dyes or multiple pollutants at a time. So what was the conclusion? Polystyrene, polyanisopropyl meth acrylamide acrylic acid core shell microgel can be prepared in 2 steps. In first step we prepare core, and in second step we construct the shell around the core, and in next step we use this core shell system as a micro reactor to fabricate the shell region with nanoparticles, and then the resultant silver polystyrene polyanisopropyl methacrylamide acrylic acid core shell microgel particles were used as a catalyst to increase the rate of reduction of different toxic compounds like nitroaromatic compounds and different dyes along with their mixture. And it was seen that our reported catalyst efficiently reduce the all toxic compounds in feasible time interval, and this catalyst can be easily recycled from reaction mixture by just mild centrifugation due to presence of a central solid core. So what are our future direction? We have aimed to remove the polystyrene core from core shell microgel system, and then we use that microsphere as a microreactor to fabricate different types of nanoparticles like copper, cobalt, or silver nanoparticles. So we assume that such type of system will show even better catalytic activity as compared to core shell hybrid microgel system due to availability of large surface area of microsphere, and as a result a large number of nanoparticle will be incorporated, and as a result their activity will be high. And we also aim to use this system as a pH and temperature sensor in future, and we will apply this system for sensing of pH and temperature in different media. And then we have some objectives to identify the products and to do further work on those products. So almost 10 papers or 10 articles have been published from these projects in international journals of good repute regarding catalysis. Thank you so much for listening.
Thank you, Dr. Khalida, for your presentation. Is anyone having any questions? Okay, I think there are no questions from anyone. Thank you once again for your presence and presentation.
Thank you so much.
Okay, so our next presenter is Dr. Federico Zaptreda from University of Ferrara, Italy. Hello, Dr. Federico.
Hello.
Yeah, are you ready with your presentation?
Yes, I'm ready.
Okay, yes, you are the presenter now.
I have to
Share
check
your-
my system preferences. Give me a second.
Okay.
Okay. Let's try. I have to restart the application. Give me a minute.
Okay.
Okay. I'm here. No, I still having problems with my screen. I don't know why. Okay. Fine.
Yes, it's visible to us. You can start your
Okay.
presentation.
Thank you so much. Okay. Good morning, everyone. I'm Federico Zapatera, and I'm working at the Biocatalysis and Biotransformation Laboratory in the University of Ferrara, Italy. And my presentation concerning the biocatalytic approach for the direct esterification of ibuprofen with sorbitol in biphasic media. Purely water-soluble drugs present outgoing challenges with their translation into bioavailable medical products. More than 40% of new chemical entities are purely soluble and so purely bioavailable. This is a great obstacle in formulation development. Thus, drugs with purely water solubility requires novel formulation approaches to improve their rate of dissolution and oral bioavailability. Among this strategy, the synthesis of prodrug with ester bound has raised attention to enhance the water solubility of active ingredients. The esterification of drugs can be carried out chemically or through biotransformation processes that involve the use of free or immobilized enzyme. The purpose of our work is to develop enzymatic esterification protocols to obtain prodrugs of pharmaceutical and agri-food uses. As shown in this slide, several active ingredients derived from different fields are purely water-soluble and so purely bioavailable. The application of lipases at the industrial level see them involved in the production of derivatives of food additives, for example, sorbic acid, chiral intermediates, or pharmaceutical products. In this work, we will focus on ibuprofen. Ibuprofen is a non-steroidal anti-inflammatory drug that was developed in the late 60s for the treatment of symptoms caused by arthritis. And ibuprofen, like ketoprofen and ibuprofen, is widely used as analgesic, anti-inflammatory, and antipyretic. Ibuprofen is a non-selective reversible inhibitor of cyclooxygenase isozyme COX-1 and 2, which are responsible for the conversion of arachidonic acid into prostaglandins, including thromboxane and prostacyclin. Due to its high patient compliance and flexibility, the most common route of administration for ibuprofen is the oral one. However, due to its aqueous solubility of just 21 milligrams per liter, ibuprofen is a purely water-soluble drug characterized by limited dissolution oral bioavailability. So the chronic use of ibuprofen orally administered may cause gastric mucosal damage such as stomach ulceration, bleeding, and perforation. Our strategy involves the enzymatic synthesis of prodrugs of ibuprofen by its union with an hydrophilizing moiety. This molecule will be a polyalcohol, in particular sorbitol. Sorbitol, less commonly known as glucitol, is a polyalcohol with a sweet taste and it's slowly metabolized by the human body. It can be obtained by reduction of glucose, but most of sorbitol is made from potato starch, or it can be found in nature, for example, in apple, pears, peaches, and prunes. Sorbitol is often used in modern cosmetics as humectant and thickener, and is a cryoprotectant additive in food. It is one of the preferred sweetening agent for its low caloric content and low glycemic index value, and this sugar alcohol is also used as excipient in formulation of various drugs and plasticizers. So we aimed to develop and optimize an esterification reaction between the purely water-soluble ibuprofen and sorbitol, representing the hydrophilization moiety of the resulting prodrug ibusorbitol ester, to obtain this prodrug enhanced in water solubility and so bioavailability. Canonically, the enzymatic esterification reaction was performed chemically by a Fischer esterification. However, instead of chemical modification, biotechnological approaches can represent green ways for the synthesis of bioactive derivatives of ibuprofen. To this end, free porcine pancreatic lipase PPL was chosen as a biocatalyst as an alternative to the more expensive, this is free PPL is an alternative for the more expensive immobilized enzyme. Lipases are catalysts belonging to the family of hydrolases, and in addition to their natural reaction of hydrolysis of triglycerides into glycerol and fatty acid, lipases can carry out esterification reaction. Indeed, lipases represent the most usable biological tool for enzymatic esterification, and since the 90s, lipases were used as biocatalysts in industry due to their high activity under mild reaction condition, the lack of need for cofactor, their synthetic activity in non-aqueous solvent, and their wide range of substrate and stereospecificity. Lipase is reported to be more advantageous, in particular this lipase, the PPL, is more advantageous than the microbial lipases in organic environment due to its higher selectivity, greater tolerance to solvent, high catalytic activity, and thermal stability at higher temperature and low water concentration. In a reaction environment in which the quantity of organic solvent prevails over the water, the lipases is pushed towards its catalytic esterification behavior, and at the interface between oil and water, the lipases undergoes interfacial activation. So PPL undergoes interfacial activation at the interface between the organic phase and the water when the reaction occurs here, and a conformational change of the catalyst occurs and increases its enzymatic activity. So the interfaces are a key spot for the modulation of the lipase activity. So the use of an aqueous organic solvent biphasic system can produce interfacial activation of the PPL. Firstly, we decided to chemically synthesize the reference standard isosorbitol ester. Then we studied the enzymatic esterification protocol and biphasic conditions such as lipase and compound concentration, solvent amount, temperature, stirring speed, and times are reported here. And finally, the lipase catalyzed sorbitol ester of ibuprofen was chemically characterized by proton and carbon NMR and mass spectroscopy. Since the target compound is not commercially available except for the unknown degree of purity, it was synthesized chemically according to the procedure in literature, and the compound was utilized as reference for the calibrations. The mass spectroscopy testifying the esterification of the chemically synthesized isosorbitol ester. So we proceeded with the enzymatic esterification. All through immobilized lipases have been shown to display better catalytic activity compared to the non-immobilized lipases in non-aqueous media. We decided to exploit and test the less expensive free-form or porcine pancreatic lipases. In a biphasic system like the reported in this work, the organic solvent had the solubilizing role towards the lipophilic compound ibuprofen, while the water solubilizes the polyalcohol sorbitol. The ability of the free PPL to catalyze the synthesis of isosorbitol ester was investigated starting with selection of a suitable organic solvent. Finding the adequate organic solvent can be challenging. Indeed, it's generally reported that solvent with log P minor than 2 are less suitable for biocatalytic purposes. Thus, based on the log P of these solvents, we choose to test hexene, benzene, and toluene as organic solvent. Ibuprofen, due to its strong lipophilicity, proved to be highly soluble in all three these organic solvents tested. There appears to be a correlation between the polarity of the organic solvent, its consequent miscibility in water, and the percentage conversion yield. This catalytic behavior of the PPL could be explained by its interfacial activation mechanism. More apolar solvent, such as hexane, having limited solubility in water results in clearer solvent-water interfaces, so the lipase has to undergo the phenomenon of interfacial activation and therefore be catalytically active. For this reason, hexane was chosen for further tests. To evaluate the effect of the enzyme concentration on the conversion yield, 5 concentration of free ppl were studied in a range from 2 to 20 grams per liter. The conversion yield increased with the amount of enzyme following an hyperbolic trend typical of the lipase catalysis esterification reaction. However, after 10 grams per liter, a small decrease in conversion yield is reported, probably in a system like the biphasic one. Since water is present in the system, at higher concentration, the lipase could hydrolyze the newly formed ester bound. For this reason, the value of 10 grams per liter was selected for the most adequate for further tests. In a biphasic system, media esterification is essential to create a neat interface between the organic phase and the water phase. So the volume of the organic solvent and water need to be finely regulated, as do for the substrate concentration and for the molar ratio. At lower water content, the enzyme activity is strongly limited by the scarcity of the aqueous compartment in the system. Probably the enzyme is not fully hydrated, and this is resulting in a decrease of its three-dimensional conformation, or water is not sufficient to generate and maintain a stable and clear solvent-water interface. At water content of 10%, a significant increase in conversion yield is observed, but where an excess of water occurs, this leads the enzyme to produce an hydrolysis of the ester bound newly formed. About the temperature, from 30 to 30 degrees, there's a net change in conversion profile of hyposorbitol esters, but after 40 degrees, a strong decrease in conversion yield occurs. This is because in a biphasic system, the presence of highly hydrophobic organic solvent is to be considered in the advent of mechanism of enzymatic instability, especially when heat is supplied to the system. The steering speed of the system is a key aspect because the interfacial area is dependent on the steering speed of agitation. So increasing the steering speed, there is an increase in the initial conversion rate of esterification. So at low steering speed, the contact between the phases is too pure to ensure the meeting of the substrate, but after 400 RPM, a reasonable decrease in conversion rate is observed due probably to enzyme instability and enzyme denaturation. When the concentration of ibuprofen increases, there's no inhibitory effect on the enzyme. However, there's no gain in the conversion yield after 60 grams per liter, so this value has chosen for certain tests. And about the concentration of the alcohol, since has been reported that the hydroxyl groups of the polyalcohol sorbitol can reduce the activity of PPL, estimating how much alcohol can be added to the reaction medium is essential. And beyond the concentration of 20 grams per liter, probably the higher concentration of sorbitol can be considered as facilitator of the protein denaturation by solvating the hydrophobic amino acid residues within the active site and stabilizing the naturated rather than native conformation of the enzyme. This reaction reached nearly 80% of conversion in 15 hours, and then there's just a little decrease. The proton NMR, the carbon NMR, and the mass spectroscopy results confirm that the lipase catalysis esterification reaction took place between the carboxylic acid group of ibuprofen and its hydroxyl group, the hydroxyl group of, there's an issue here, of sorbitol. The esterification products formed had a predicted mass of 370, and the fragmentation pattern showed in the slide described the mass of isosorbitol ester as the ionized protonized adduct and sodium adduct. So, in conclusion, ibuprofen is a widely used anti-inflammatory drug limited in bioavailability by its poor water solubility. In this work, we proposed an effective optimized esterification process for the production of the enhanced water-soluble ibuprofen sorbitol ester. This direct esterification route has been optimized for biphasic media dynamics, enzyme concentration, water content, temperature, stirring speed, substrate concentration, and reaction time. Proton and carbon NMR and mass spectroscopy confirmed the PPL catalyzed esterification of ibuprofen with sorbitol, and to the best of our knowledge, this is the first time that enzymatic esterification of ibusorbitol ester has been proposed. This is my references, and thanks to my colleagues that shared with me this work, and thanks to the organization. Can you hear me? There's someone?
Yeah, hello, Dr. Federico. Thank you for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation. Okay, so our next presenter is Dr. Maria Mercedes Icart from National Institute of Agricultural Technology, Argentina. Hello, Dr. Maria. Are you ready with your presentation?
Yes, hello. Good morning for
Good morning,
people
yeah.
this side of the world. Good afternoon.
Okay,
For the
you
rest.
are the new presenter. Please share your screen with us.
Yes, I hope so. Oh,
Yes, it's visible. You can start your presentation.
okay. Let me put this in. Sorry. I cannot share the whole picture.
No, your screen is visible to us.
Okay. Do you see the full
Yes.
presentation? Okay.
Yes.
So thank you. First of all, thank you for the invitation. And I want to thank the organizers. I am quite surprised because, and I apologize because I will take you from the micro world to quite a macro world. And the work I will show you today is entitled Towards an Ideotype for Food Biogas Dual Purpose Wheat in Argentina. And first of all, I want to, how do I go forward?
Sorry?
Arrows are not working. How do I do this?
What? Yes.
How can I advance my presentation?
Yes, you can click on the slideshow button at the bottom of your screen.
I don't see it.
I think F5 will work and your presentation will go on.
I'm sorry,
Please.
can you repeat?
The F5 button will run your presentation to whole screen. F5.
F5.
Or Shift plus F5, I don't know.
Shift plus F5. No, nothing occurs.
It's not working. Okay, sorry.
Ah,
Yes, yes.
okay, I am looking. Do you see the next slide? So it
Yes.
worked. Okay.
Yes.
So first of all, where is Argentina? Argentina is the southest country in South America. It is a large country where agriculture is one of the most important economic activity. And together with soybean and maize, wheat is one of the most planted crops. Here you can see some figures that picture what wheat means for Argentina. As you can see, last year, 6.5 hectares were planted with wheat, and wheat reported 3% of national exportations income and 3.4% of agriculture gross product. There is a small area in Argentina that is devoted to wheat crop. So Shift F5.
Now you just use arrows.
No, it's not working with arrows. What about down arrow?
No, as a side arrow or down arrow, or you can click on the mouse as well. It will go to next slide.
It's not working. I will escape and go again.
Yes.
What about now?
Yes.
Okay. So further than the importance of wheat grains for food production, wheat straw is one of the most available lignocellulosic residues in many countries, including Argentina. So wheat straw has multiple applications that include use of animal bedding, mushroom production substrate, and feedstock for biomass burning power stations. And a significant amount of wheat straw can be used as a feedstock for many biofuels, including biogas. And when you use lignocellulosic biomass for bioenergy production, you call it second generation feedstock. And the advantage of second generation feedstock is that it doesn't compete with food production. So Argentina produced last year 20.2 tons of grains and also 26.3 tons of straw. So we have a lot of straw that could be directed to bioenergy production. And among biofuels, biogas is known to be a biofuel that is produced with a technology that is highly efficient and environmental and socioeconomical friendly. I'm sorry, I will go back. So growing wheat with the dual purpose of producing grains and straw offer the possibility of increasing the resources available for biofuel production without compromising existing food production. So further than increasing maybe farmers' income, biogas production contributes to reduce greenhouse gas emissions and ensure energy security in the rural sector. And what is biogas? Biogas is a mixture of methane, carbon dioxide, other minor gases, and water steam. I think methane is the molecule that brought me to this webinar. And it is produced during anaerobic digestion of organic matter. And how is it produced? Biogas can be produced from many different feedstocks, including livestock waste, crops, wastewater, and food waste. In the case of our work, we point out to the value of wheat straw to be transformed into biogas. So feedstocks are introduced into a digester, that is a reactor that is deprived of oxygen, and by the concerted action of many microorganisms, it is turned to biogas and dish state. Biogas is a gaseous stream that can be transformed into biomethane or directly used to produce heat or electricity. While dish state is the liquid fraction of the process that can be used as fertilizer, closing the loop of nutrients utilization in a circular economy scheme. Recently, Townsend et al. Described what are the key traits that should be considered to be able to use wheat as a dual purpose crop. So an idiotype is a plant that gathers all the best traits or the best values for the traits in one plant. So a wheat plant should have a high grain yield, high straw digestibility, and low lodging susceptibility to be considered a good material to be grow for dual purpose use. That dual purpose includes food and biogas production. And wheat straw is made up mainly by plant cell wall, and plant cell wall in turn is a complex and recalcitrant structure that is formed by microfibrils of cellulose, lignin, and hemicellulose. This complex structure makes difficult the wheat straw to be digested and transformed into biogas. But still, it has a lot of sugars that can be converted in many forms of biofuels, like bioethanol or biomethane. So the aims of our work were to determine the best food fuel wheat idiotype candidates among 36 wheat genotypes that are currently used in breeding programs in Argentina, and to give some insights into the relationships between key traits relevant for dual purpose wheat genotypes. To achieve those aims, to address those aims, we explored those key traits in 36 genotypes that we classified according to their germplasm, according to the origin of their germplasm, and divided them into French criollos that are local germplasm and CIMID ones. And among them, we also classified genotypes according to their grain yield into low and high yield, depending on whether they overcome a threshold of 4 tons per hectare. So we observed what were the values of grain yield, what were the values of straw yield, and what about the harvest index, that is a parameter that allows to measure how much plant is going to form grains and how much is going to form straw. And we also explore lodging susceptibility, that is a trait that precludes wheat harvest if it is a problem in the culture. So here I show you the values of grain yield in blue and the straw yield in red for the 36 genotypes, and continuous lines represent 90% percentiles. 90th percentile of those values, and we decided that those genotypes that could overcome that threshold could be considered genotypes of outstanding grain yield or straw yield values. So we detected 3 criollos genotypes, Bucbachiano and Bucguapo, and 1 French genotype that complied with this premise. If we lower down our threshold and establish it as 17th percentile, we could detect many other genotypes that could comply with the double condition of having high grain and straw yields. We explore what about biomass allocation, and we observed that CIMID and Criollo genotypes behave in the similar way, while French genotypes differed from them in that no matter what the size plant was, plants delivered always the same proportional amount of biomass to grains and to straw yield. So looking at these graphs, one could see that it makes no sense to try to increase grain yield in cement and criollo materials, genotypes, because increasing grain yields decreases straw yield. By the opposite, when breeders would try to increase grain yield in French genotypes, straw yield increases together with grain yield. So French materials are the best candidates to be included in breeding programs that are meant to increase both straw and grain yield at the same time. We also measure some interesting morphometric traits that are stem diameter, stem wall thickness, plant height, and dry spike weight. And with all those values, we could calculate load-chain susceptibility index according to Mirabella et al. And we observed different interactions between grain yield and origin on all of these traits. But the most important thing to say is that when we establish a 10th percentile, that is inverse of 19th percentile, because the lowest the load-chain susceptibility, the better the characteristic of the plant. And we observe that only 4 genotypes comply with the condition of displaying low load-chain susceptibility, and all of them were of French origin. If we define that threshold as the 25 percentile, other many genotypes could comply with this condition. Further to agronomic traits, we explored how about straw quality to be digested to produce biogas. And for that, we determine cellulose, hemicellulose, and lignin concentration in straw. And we also ran biogas production tests. In that case, we put some wheat straw together with the bacteria that are able to transform that wheat straw into biogas, and register recorded the accumulated methane along the time, and adjusted and fitted this model that considers a first order kinetic of increase in methane with time. Here, it is interesting to know that these two parameters, Bmax and K, give important information regarding wheat straw digestibility, but also are useful to design reactors when you plan to include straw as a feedstock for biogas production. And we related those parameters with straw composition because we know that biomass digestibility is related to lignin content, to cellulose crystallinity, and to hemicellulose content, but not only to those individual components, but it relies on the interaction between among these components. So we found that the maximal volume of biogas attainable increased with cellulose and with hemicellulose, and it did not depend with lignin, depend on lignin, while the rate of digestion, which is determined by K, that parameter K, was inversely related to cellulose and hemicellulose, while the dependence of K with lignin was not significant. And among the interactions that were relevant for for kinetic parameters of biogas production, we found that cellulose to hemicellulose ratio was important mainly for K parameter and when we consider high lignin content. And this could be explained by many things that we previously have observed. The first one is that lignin is known to cause a more severe inhibition of methane production from cellulose than from hemicellulose. Then lignin encrusted cellulose cannot be reached by cellulases. So when we have more cellulose, not necessarily we could achieve more biomethane. Hemicellulose, by the other way, has been shown to reduce lignocellulose crystallinity. So if we have more hemicellulose in the biomass, maybe we could counteract lignin's inhibitory effect on biomethane production. And finally, we analyze oil trace together in a principal component analysis. And here you can see in this figure the plot of the analysis. Principal component 1 is determined mainly by grain yield and straw yield, which we found that are highly correlated, and somehow by Bmax parameter. While PC2 is mainly explained by K parameter, and in a lower extent by Lodging susceptibility and Bmax. Some interesting results obtained from this plot are that there are very few materials that can be considered candidates for dual purpose use. These 4 materials that you can see rounded in the dotted line are 2 French materials and 2 Criollo materials, and then they have some good performance in some of the traits, but not in all. So French materials that are Nogal and Baguette 31, they have very high grain yield and straw yield, and also a low lodging susceptibility, but their performance in biomethane kinetics are not so good in any of each one. While in Criollo genotypes, Buc Baquiano and Buc Guapo, they also showed high grain yield, high straw yield, but they are susceptible to lodging, so they are not good materials to be grown in soils that are not too deep. By the other hand, if we point out to materials that are quickly transformed into biogas, we can detect that Baguette 21, BI 1003, and Baguette 10 are good materials to obtain rapid transformation of organic matter into biogas, but the problem they have is that they don't present high grain yield or straw yield. And we detect an area where acceptable values for all traits can be found. So in particular, genotypes 6, 19, 6 and 28 in the dotted line developed key traits that were all over 50th percentile. So as a conclusion, we found high variability in key traits for dual purpose wheat idiotype for food and 2G biofuel, biogas in this case. None of the genotypes excels in every key trait, but a few candidates presented acceptable values in many of them. And particularly 2 genotypes of French origin resulted best candidates among current available materials. So the challenge for breeders lays in attaining a genotype with excelling values in all key traits, and breeding efforts in this direction will increase the resource available for lignocellulosic biofuel production without compromising existing food production. And that's the picture of our experimental station here in Argentina. And thank you for your attention.
Thank you, Dr. Maria, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation.
Thank you.
Okay, moving on to our next presenter is Dr. Elka Madhukar Thacker from Vet University, UK. Yeah, hello, Dr. Elka.
Hello,
Are you ready
good
with your
afternoon.
presentation?
Yes, I am.
Okay, so you are the presenter now. You can share your screen with us. Yes, it's visible. You can start your presentation.
Hello.
Yes, your screen is visible to us.
I cannot see it.
You cannot see it?
No,
I'm sorry, like we can able to see your screen.
but I lost the screen where I was currently.
I
Why
might
don't
you have to close the window. You can start your presentation once again.
yeah, I will start it again.
Okay.
Do I have to leave the meeting and come back?
No. You can do it on your screen itself. Please click on the presentation you have saved, wherever you have saved your presentation. Can you please close this Word document if it is not your presentation?
Oh, you can see this.
Yes, we can able to see your screen.
Okay, okay, okay,
Yes. So now you can click on your presentation.
okay.
Yes.
Yes, is it visible?
Yes.
Okay. Okay, hello and good afternoon to all. I am Alka and my ongoing PhD is focused on sustainability in textiles, and here it is condensed towards applied green chemistry, wherein we are working with pigments from plants for both the functionality and coloration on textile fiber fabrics. The characterization of plant pigments by itself is massive. I have just listed a few over here with some examples that I have cited that are in direct application for textile substrate, and they are utilized since ancient times. Currently, they are under review and under focus as they propel sustainability in textile. It could be noted that the flavonoids, anthocyanins, are very large among them, and besides these, there are tannins, alkaloids, of which tannins are again a very large group of pigments that are utilized in application for textiles. We can now look at its progression towards how we do the processing of it in the laboratory, wherein we extract the colors from plants and we perform the reactions at low temperature, room temperature. This is again for deriving the ecological outcomes. The further analysis of this extract solution is done, as well as the treated fabric is done with the help of FTIR and other techniques as well. I am focusing here significantly on ATR FTIR as it is helpful in analyzing the functional properties, the functional group that exist in the extract solution, the bioactive plant phytochemicals that exist in the extract solution that are transferred onto the final fabric on application. Let's look at how we go about doing it. What we do is we take the raw herbs, we dry them, we mill them, and we obtain the extract solution. Here again, I would like to bring to notice is that we are utilizing pure distilled waters. We are eliminating the use of alcohol-based solvents and any other solvents. This is again to propel sustainability in textiles for ecological outcomes. And as you can notice, we experimented with merino wool fibers, banana fibers, and bamboo fibers. And to facilitate the further test procedures, we do the same application process on merino wool yarns, which we take on to further analysis and testings. The ATR FTR analysis, as we can see, of the raw herbs. Here I am considering two. I am giving the example of two. Recently we had experimented with 21 herbs. Of these two herbs, one is as noted is mango ginger. The ATR FTR analysis of the raw herbs is taken and the treated fabrics is taken, and it very distinctly gives the results where you can identify the dense functional groups that are there. Here I am citing two examples. One is the mango ginger and other one further ahead will come is the cloves. Now from the two, it has been identified that mango ginger is very dense in phytochemicals and the cloves as well. The cloves is more dense in phytochemicals as compared to mango ginger, but the principal and predominantly functional groups that are dominating in those are noted here. And they are the conjugated bonds and the triple bonds, which strongly adhere to the fabric substrate. And what is happening in the process is the entire green chemistry that inherently exists in the herbs is transferred onto the fabrics. And that makes the resultant fabrics functional as well. One of the interesting things that we analyzed further was with regards to the spent solutions, the leftover herbal solutions after processing the fiber fabrics in it. We tested it for its oxidation reduction potential and dissolved oxygen levels. This is to support our hypothesis again of the sustainability processing. And as you can note the values, these values are in the acceptable range, and that makes them suitable to be safely discharged into any water bodies after the processing is completed. And all the more, what is significant is they are completely completely capable and completely in a position to be recycled, reused, and upscaled. Had this been with the fossil-based colorants, the values are all, in an unacceptable range. I'm not doing a comparative study, hence I'm only focusing on the results with the herbs. This encourages the sustainability goals, the SDGs, where we are protecting the life on water and life on land. Here, the slide represents is the color values, which are important when we are applying it onto the textile substrate. It gives us the absorbance values, the extent, the indication of the depth of colors, the lightness and darkness, the redness and the yellowness part of the colors obtained from these extract solutions onto the textile substrate. Here the figures are given on for when they are applied onto the merino wool yarns. And as obvious, the color range for the mango ginger is towards the yellow, and for the cloth, as you will see further ahead, is in the range of brown. Here I come to the fastness ratings, which gives us an idea of how adherable is the colorant from the extract solutions, how well the phytochemicals have adhered to the textile substrate. And it is done with the help of RotaWash for the wash fastness test and TrueFade for the light fastness test as per the British standards. And as you can see, the values obtained are very good for cloths, except for the light fastness rating, which has gone down for mango ginger. And this indicates us to process the fiber fabrics of mango ginger in shade. A shade drying is recommended for the purpose. This figure gives us a clear picture of how the chemical bonds are taking place in the fabric fiber matrix, the microfibrillar structure of wool, and how the phytochemicals existing in the plant pigments are adhering to the wool fabrics, whereby they form a complex, and this complex makes the resultant fabric functional. The phytochemicals are inherently bioactive, which perform the functions of, as mentioned over here, antibacterial, antifungal. And when they are applied onto the fabric substrate, the properties are transferred as well, which is confirmed further by the clinical investigations. Additionally, they are also soft to skin and aromatic to the wearer. Let's look at the second example that I have dealt with, where I have considered cloths for the application on the merino wool fibers, banana and bamboo fibers as well. In a very similar way, the chemical bonding is taking place, wherein the conjugated and triple bonds make the phytochemicals adhere to the microfibrillar structures, and they perform the fabric of being insecticidal and antibacterial and others of the resultant fiber fabrics. What I'm trying to say is that the entire thing that is happening from beginning till end is an example of biomimicry. It is an inspiration from nature that we are utilizing to solve our existing problems of climate crisis, human health and environmental health, emissions and effluents, life on land and life on water problems from textile emissions and effluents, especially from the coloration unit, wherein the green chemistry is playing significant role. And in the entire processing that we have dealt with here, you can see the ideologies of green chemistry being applied, wherein no waste is generated, all the synthesis of chemicals is plant-based, there are no additives and auxiliaries. We have not even utilized the mordants, which eliminates the use of any additives and auxiliaries. And yet you can see the fastness properties, the color values obtained are in the acceptable range, and the ORP and DO. The plant-based materials are completely renewable. The reactions are carried out at room temperature and below 50 degrees Celsius of temperature. There are no modifications or postulates involved. And very importantly, they are biodegradable at the molecular stage itself. And they are environment and human health safe. The entire concept is an excellent example of biomimicry, as I mentioned earlier. I would just like to end with a quote wherein is inspired by Sir Albert Einstein. Look deep into the nature and you will understand everything better, as I did with the entire working with my plant pigments and herbal biomaterials for textile applications. And it all propelled us towards sustainability. As a future scope of research and development, life cycle analysis and clinical investigations are to be performed. Here are some significant references, and I'm grateful to both the Coalesce Research Group and Heriot-Watt University for giving me an opportunity for this presentation on plant pigments and its application on textiles. Thank you so much.
Thank you, Ms. Alka, for your presentation. Is anyone having any questions?
Yeah, I would be grateful if you have any questions, I would take it.
Okay, no questions from anyone.
Okay, thank you so much.
Okay, thank you. So our next presenter is Dr. Romina Romero from Universidad de Tarapacá, Chile. Hello, Dr. Romina.
Hello, can you hear me?
Yes. Are you ready with your presentation?
Perfect.
Okay.
Okay.
Yes, you can share your screen with us.
Okay. Let's go see. Please,
yes,
can you tell me? Okay. Now you are watching us presentation? Yeah.
Yes.
Okay. So I will start. Good afternoon to all. My name is Romina Romero, and I will present my work today entitled Removal Persistent Pollutants by Phantom System, Enhancing Degradation by Bio-Based Chelating Agents. Is very well known the big availability of forestal resource biomass in the world and the increasing interest in its fuel liberalization. In the case of Chile, Chile is a country, it's a thin and large country located in South America. And the forestal resources are a very important economic sector on the country. It's estimated about the 59% of all forestal plantations are Pinus radiata. According to the forestry industry, in the production chain are a lot of biomass losses. So it's estimated that the bark in the Pinus radiata is about the 10% of the weight of the tree. So has been estimated that there is a generation about 3 million cubic meters per year of this biomass resource of pine bark. The pine bark is composed by cellulose, hemicellulose, lignin, and extractables. In the extractables, we have tannins, waxes, resin acids, and other compounds, but the most important, that is near of 60% of these extractables, are phenolic compounds. These phenolic compounds can be water-soluble or water-insoluble. The water-soluble are hydrolysable tannins, and the water-insoluble are condensate tannins. So currently, the fraction that is water-soluble is used in the country by generation of wood adhesives. But for this purpose, the water-insoluble fraction must be extracted because it's like an impurity for this fraction to have a strong cross-linking for the adhesive. So currently, this fraction that is insoluble in water don't have any application. So for us, this was an opportunity to develop some research knowledge and also innovation. In 2014, Case et al. Published a work of micropyrolysis for this polymer, for water-soluble tannins and for water-insoluble tannins for both fractions. And they found the methyl catechol and catechol were the major products. However, this work cannot be compared with another biomass source like lignin or bark or wood, because these tannins were pre-treated with a formate solution. So this can change finally the yields of these compounds. So after we, in 2018, we published this work that we compare different biomass sources like lignin pine, untreated pine bark, where this was isolated the water-insoluble tannins and water-insoluble tannins, and our interest fraction, that is water-insoluble tannins. So we compare our results, and we found that, for example, for lignin, the major products were acids like acetic acid and guayacols, but the catechol content was only near of 3%. So after we studied the pine bark, in this biomass source, we can see here that we have a higher yield of catechol and methyl catechol, but a big disadvantage of this system is the higher yield of carbohydrate compounds, because the carbohydrate compounds will influence the purification steps to use the phenolic part of the pine bark. So the extraction that is used previously to extract the water-soluble tannins for wood adhesives become an advantage for us, because it's like a pre-treatment for our phenolic part. And we can see here that now we have the major thermal decomposition products are the catechol and methyl catechol, but we don't have the influence of carbohydrate compounds. In this fraction that the water-insoluble tannin, only near of 2 or 3% of carbohydrate were found. So after we perform NMR analysis, and we compare our shift movements with the literature, and we found similar signals. This is performed in solid phase. We found similar behaviors to reported previously for another types of pine bark. And the most important thing in this analysis was this signal in the number 5, because the number 5 told us which is the disposition of the polymer between the monomers linked. So we propose with these results that our polymer, that is condensable tannin, is linking catechin units between the carbon 8 and carbon 4 in major proportion, but is reported also that can also be this union between 6 and 4. But according to our results in this fraction of water-insoluble tannin, we are looking more this structure. After, for compare this monomer that was catechin with the polymer was water-insoluble tannins, we compare the ultimate and proximate analysis. So we can see here there are very similarity between the catechin and water-insoluble tannins, for example, in the carbon content, hydrogen content, and oxygen content. So this allows to propose that, okay, we have a lot of bark. An important part of bark is used now to develop wood adhesive, but is another part that don't have any use and is considered as an impurity for the system. So We know now that this is conformed by linked catechins in this conformation, and now we need to look for some application. So the big particularity that have this polymer is this ring here. It's a B ring that have a catechol type here, and these kind of phenolic compounds are able to complex different kind of metals. So we propose the use of this ring for advanced oxidation process. The catechol himself have been broadly studied and is incorporation in these processes because enhance the production of free radicals, also the catechin. So our proposal is use this insoluble fraction, taking advantage of this available B ring to complex metals to the generation of free radicals for water remediation for different pollutants. So one of the most important advanced oxidation process is the Fenton reaction. The Fenton reaction is produced when iron is reacting with hydrogen peroxide. The iron is oxidized and is produced hydroxyl radical. Hydroxyl radical is one of the main oxidizing species, but also this system can produce another kind of radicals like superoxy radicals and singlet oxygen. If you are not using iron 2, if you are using iron 3 or another metal, you will have a Fenton-like system, okay? And the system, very fast to describe, when you have iron 2 and hydrogen peroxide in solution, you will produce hydroxyl radical, okay? But the big problem of this reaction, here is the conventional Fenton compared with the reaction driven by catechol or 1.2 dihydroxybenzene, that is the generic name for these compounds. We can see here that, well, the oxidation of iron to iron 3, that is the Fenton reaction, is very, very fast. However, the reduction of iron 3 to iron 2 is very low, okay? So the redox cycle is very limited by this step. But when some organic ligands are used, we have that is favored the reduction of iron. One of these organic ligands that have been studied are the catechols or dihydroxybenzenes. So here in this cycle, redox cycle, the hydroxybenzene will be oxidized to semiquinone and then to quinone, and this will allow to the reduction of iron 3 to iron 2 faster than in the conventional reaction. So this reaction has a strong pH influence because only the monocomplex, this means only with one molecule of catechol or dihydroxybenzene, you will have more production of hydroxyl radical. But this must be to acidic pH. On the other hand, when you have a near neutral pH, the vis complex, this means two molecules ligated to the iron, will be produced more iron 4. And in the case of the tris complex, that is unit to 3 units of dihydroxybenzene, this is an antioxidant system. This did not allow the reduction of iron 3. So we have, depending of the reaction conditions in Fenton system, driven by catechols or 1.2 dihydroxybenzenes, two kind of behaviors, antioxidant capacity or pro-oxidant capacity, where the antioxidant capacity will follow this mechanism of radical trapping or iron ligand, and the pro-oxidant capacity, this means that produce more free radicals, will be follow the mechanism of iron reduction or oxygen reduction. So the big drawback of this kind of system is the oxidation, finally, of the dihydroxybenzene to quinones, because in this system, these quinones will be released to the treated water. And the big problem of these molecules are that very toxic and cancerogenic. So we are proposing the opportunity to use these catechol or dihydroxybenzoate that are insoluble in water to include in the Fenton system. So we are proposing to fix the iron over this matrix, polyphenolic matrix, and then perform Fenton reaction to produce more free radical species that can degrade any pollutant. So the reactivity of this system will be measured according to iron reduction and also to radical species production and also degradation of different pollutants. In the first case, that is the heterogeneous Fenton reaction, when we measure the iron reduction, we will have when the technique of iron with ferrocene form a complex that is visible by UV-vis spectrophotometry. And we can see here, if you have more iron 2 available to complex with ferrocene, you will have more absorbance, okay? So after 24 hours, we compare the results of catechin, that is homogeneous Fenton system, and water-insoluble tannins that is in a heterogeneous Fenton system. And after 24 hours, we observe that in the case of water-insoluble tannins, reach higher amount of absorbance of this complex. This means that this system that is driven by water-insoluble tannin have more efficiently reduce iron 3 to iron 2, more than catechin system. After we tried the model pollutant degradation over methyl orange to compare the constant rates according to comparison with Fenton-like conventional, Fenton conventional, and one driven by tannins. We can see here how significantly the amount of the constant rate increase when tannins are added to the solution. After we measure the radical production, principally hydroxyl radical production, according to speed trapping technique in EPR, where we use the measure of an adduct between DMPO-OH in EPR, and this is the characteristic signal of this adduct. And we compare different systems, and we can see here that all the system show the characteristical signal. However, the system driven by tannins show the most big or the highest signal. And have been reported previously that the height of this signal is directly related to the amount of activated species. So we can conclude of this say that this system have more activated species than the other system. After, as the EPR technique by spin trapping, the adduct between DMPO and OH is very unstable. This is not allowed to measure the hydroxyl radical production in longer times. So we propose the use of HPLC with detection of fluorescence using the selective hydroxylation of coumarin to give 7-hydroxycoumarin, which is detected by HPLC fluorescence. So this allowed to us to compare the different system, but in longer times. We can see here that the trend obtained is the same observed in EPR. So the Fenton system, like driving tannins, is the most higher production of this compound, that is the 7-hydroxycoumarin, that is directly proportional to the amount of hydroxyl radical. So our system is more efficient in iron reduction and also in generation of hydroxyl radical. This allowed to us to propose this redox cycle, where the rate limiting step is the iron reduction. So the iron reduction, where is complex by the catechin or insoluble tannin, will be reduced by an inner phase sphere transference. So one time that is free, this iron 2 is available again to react with hydrogen peroxide and generate hydroxyl radical. This allowed to measure the degradation of atrazine, and we perform the kinetic controls. And here in the kinetic controls, we take off one variable. For example, one was without tannin, another was without iron, and another experiment was without hydrogen peroxide. We can see here there is no degradation in the controls, but meanwhile, in the case of phenton-driven tannins, in 30 minutes, we have near of 97% of degradation of atrazine. So taking these preliminary results, we perform experimental design to optimize the condition, and we obtain that the condition optimal for this heterogeneous phenton was pH 3.6, and this concentration of tannins, hydrogen peroxide, and iron. But the most important thing here was the quadratic dependence of the pH over the system. There is the only quadratic influence over the system. So in this optimal condition, we perform again the mineralization, and we obtain after 30 minutes, it is the minimal concentration of atrazine. After we studied the degradation products by GCMS, we took the aqueous solution and we pre-concentrated by solid phase extraction, and we analyzed by GCMS, and we obtained only degradation products that are coming from atrazine. We don't obtain any aromatic or polyphenolic compounds that can come from the tannins. Only the degradation products are coming from atrazine, and a very small amount. This allowed to us to propose which are the degradation pathways according to tannin degradation. And this is very important because we use this solid, but we try to see which was the life cycle, and we took after one degradation, we filter the solid, and we wash it and we dry it, and we use it again for a consequent cycle. And the supernatant, that there is the water, was pre-concentrated and analyzed by GCMS in order to find some degradation products that are coming from the tannin and not from the pollutant. And the results showed that similar oxidizing ability exists after each cycle. And also, no compounds, aromatic or phenolic, were detected in the GCMS. So one of the main drawbacks of this system that is presented here is the narrow pH span and instability of hydrogen peroxide. So our future direction in this work is we are working now with in situ generation of peroxide, hydrogen peroxide, according to the reaction with calcium peroxide, because we look according to a bibliometric search with phenton, what's the water. We are going to the research, we're pointing the research right now, and we observe that chelation is one of the main tasks that will resolve it. So our proposal is still working with these organic compounds, because in preliminary results in phenton system using this in situ generation of hydrogen peroxide, we observe what in the system that have some organic chelant like catechol or tannin, we observe a slower growing of the pH. This means that allow a degradation by Fenton system be more efficient in pH that being near neutral or acid. So this system reach a higher rate of degradation than the system that don't have these organic ligands. Thank you for your attention, and any question, please feel free to just ask it.
Thank you, Dr. Romina, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation.
Okay, thank you very much.
Okay. So moving on to our next presentation, it's from Dr. Matthias Bonisch from KU Leuven, Belgium. Hello, Dr. Matthias. Are you ready with your presentation?
Yes, hello. Thank you.
Yes.
I'm ready.
So you can share your screen with us.
Yeah, give me a second.
Yes, it's visible.
Okay, great. All right. So, yeah, thank you for the invitation to present here. So I will be talking about titanium alloys and in more particular about phase transformations that occur in these alloys and their thermal expansion. So it turns out they have a very peculiar thermal expansion, in fact. And I will go into this in a bit more detail. I'm based at KU Leuven in Belgium. And this work is a collaboration, in fact, between various institutes and universities across Europe, in fact. So there's the Leibniz Institute, the IFW in Dresden, also the Technical University of Dresden, University of Vienna, DSRF, so the synchrotron in Grenoble, and the funding comes mostly from the European Union. Before I start, I would like to say thanks to my collaborators and well, supervisors and people who contributed in one or the other way from the aforementioned institutes, and also the funding through the through an FP7 project by the European Union. So I will first give a short introduction on beta-stabilized titanium alloys. Why do we study them, and what makes them special? Why are they interesting? And then I have two results parts. The first one is about phase transformations, and especially about diffusive pathways in these alloys. And I'll be talking there about thermodynamic calculations and predictions of precipitation pathways, and then in situ experiments to verify these predictions. And a second result part will be on tailoring the thermal expansion of these alloys. Turns out that they have one, or not even one, it's the largest thermal expansion of a solid material ever recorded, and then ways how to use this to control thermal expansion of macroscopic samples. So, saying a few words about titanium alloys in general. Depending on the alloying element that is added, we see different types of phase diagrams in the system. And let me see if I can get a pointer here somewhere. I don't see one here. Okay, just continue like that. So we can classify alloying elements into beta stabilizers and alpha stabilizers. And the beta stabilizers, as their name says, they stabilize the beta phase of titanium. So the beta phase is the high temperature phase, which is a BCC, a simple BCC lattice. And so adding these elements, so for instance, chromium, iron, copper, silicon, tungsten, vanadium, molybdenum, and so on, they pull down the beta transits. So the beta phase is then thermodynamically stable at lower temperatures. In contrast, the alpha stabilizers, they stabilize the low temperature alpha phase, which is an hexagonal HCP phase, and they increase the temperature range in which alpha phase can be found. And typical examples for these, for alpha stabilizers, are aluminum, tin, and also interstitials like oxygen and nitrogen. And in the following, I will focus on niobium, which is a beta stabilizer. And it has, in fact, a very simple phase diagram. So these type of alloys, we also call them beta isomorphous alloys, because they only have two stable phases, that is the alpha and the beta phase. And vanadium, niobium, molybdenum, tantalum, and tungsten, they all produce this type of phase diagram. Yeah. And they all have similar properties. What makes them different is the intensity or the strength by which they stabilize the beta phase. So for some of these elements, we need fewer or less content to stabilize the beta phase than with others. And so we have two stable phases in these alloys, the alpha and the beta phase. And so we have a very broad two-phase region where alpha and beta phase can coexist. And because of this very broad two-phase region, we also have a lot of metastable phases or metastable states that can occur when we do thermal processing of these alloys. So there are martensitic phases that form by rapid cooling. These are denoted alpha prime and alpha double prime. Alpha prime is a hexagonal phase. It's basically the martensitic version of the alpha phase. And alpha double prime is an orthorhombic martensite that forms at intermediate beta stabilizer content. At the higher stabilizer content, beta stabilizer content, the beta phase can be obtained at room temperature in a metastable state, or then also in a stable state if we add enough beta stabilizer. And in addition to that, we have omega phase, and this omega phase can form in various ways. So it can form via diffusion, it can form diffusionless, so during rapid cooling, but it can also form by application of pressure. So this omega phase is in fact also the high pressure phase of titanium, of pure titanium. So in case of titanium niobium, the situation looks like that. So we have an extremely broad alpha plus beta two-phase field here in blue. That's the stable phase diagram. And then we have a metastable phase diagram on top here in green that is due to the omega phase. Yeah? And so when we perform heat treatments on these alloys, we have various competing phase transformations that take place simultaneously, in parallel, or directly after each other. So the thermal history of these materials is very important when we want to tailor their microstructures and mechanical properties. Now, in titanium niobium, what makes it even more interesting is that the diffusion is extremely slow. Yeah, and so it turns out that below 800 Kelvin, it is almost impossible to obtain true equilibrium. Yeah. Thus, as already mentioned, our microstructures are extremely sensitive to the thermal history, and we have a lot of competing phase transformations in the systems. Now, the question about a correct thermodynamic description of this system is not yet completely answered. Yeah. So when we look at into the literature, we find different descriptions or thermodynamic models that describe these phase diagrams. And there's a recent a model published in 2016 by Jan and Olsen that in fact proposes or postulates a stable miscibility gap in the beta phase. Yeah, so that's here shown in red on the right. Yeah, while previous thermodynamic descriptions don't have this stable miscibility gap. So there is some discrepancy and yeah, discussion going on in the literature. What is the correct description now here? But nevertheless, we can use these free enthalpy landscapes to look into potential transformation pathways. And this is what we did here. So looking at the how the Gibbs free energy behaves for the omega phase versus alpha phase and the beta phase as a function of temperature and niobium content, we can identify specific reactions that take place in certain composition ranges at certain temperatures. So I've shown here 3 of them. So an omega alpha cascade, then the formation of isothermal alpha double prime, and the decomposition of alpha double prime martensite. So the omega alpha cascade, that is something that's already long known from the literature, where in the beta phase, omega phase forms first, and then at a later stage, alpha phase. Yeah. What has been only recently been discovered is, in fact, the formation of isothermal alpha double prime. Alpha double prime has previously been known to form only in a martensitic way during rapid quenching. However, with in situ experiments, and I will show one of these later on, we can in fact observe a formation of an orthorhombic phase also during isothermal heat treatments or during precipitation reactions, even during heating. So it's obviously not a martensitic phase anymore. And so this phase occurs when the beta phase is thermodynamically unstable enough, let's say, and this phase then forms as an intermediate state during alpha precipitation. And a third reaction that is very interesting to look at is the decomposition of martensite, which has been also proposed by many to occur in a pseudospinodal way, where composition fluctuations simply strengthen each other or grow and become stronger. So and our challenge is to, in fact, confirm these reactions by experiments and to verify our thermodynamic descriptions. And this is by far not an easy task, since the involved volume fractions can be low, and these phases can, in some cases, exist only for a very short amount of time and in very low volume fractions. So how do we go about that? So we prepared a series of binary titanium niobium alloys with compositions that cover the entire range of martensites, up to the metastable beta retained at room temperature. So that would be for alloys with about 48% niobium. We have beta phase obtained at room temperature, and for lower niobium contents, we see martensite either alpha double prime or prime. And here on the right, we have some example microstructures for these martensitic and partially martensitic and purely beta alloys. Now, when we heat these alloys, there are a bunch of phase transformations going on during heating, and the phase transformations they depend on the composition. So we have for low niobium contents, we basically see that at one point the martensite decomposes. So that is here the reaction 1. In fact, that is martensite decomposition, where some volumes become denuded or lean in niobium and others enriched in niobium. And finally, alpha and beta phase, the equilibrium phases form. But then we have intermediate compositions where there is a reverse martensitic transformation, and directly after that we have some omega phase precipitation, and the omega phase then again transforms back into beta. These are quite complex transformation reactions, in fact, and they take place simultaneously in parallel. And so to identify and to unravel them is quite some work, in fact. But so we can observe, in fact, all these 3 reactions that I mentioned before. So we can, in fact, observe with in situ methods the decomposition of martensite. We can also observe the formation of isothermal alpha double prime, and also the omega cascade. I will show on the next slides then the in situ experiments that allowed us to identify these reactions. The in situ experiments were done using high energy synchrotron X-ray diffraction at the ESRF in Grenoble. You can see here a photo of the experimental setup. So that was a heating stage with a 2D detector behind it. So in principle, a quite basic experiment, and the diffraction patterns were then simply integrated into full, along the full azimuth to obtain one-dimensional patterns, and on these then we performed Rietveld refinements and extracted the volume fractions. We performed Rietveld refinements, extracted the volume fractions, lattice parameters, and so on. Here in the bottom are 2 examples for 2 different compositions, and simply by looking at which intensities appear, how they shift, how they disappear, we can follow the evolution of the material during heating and also during cooling. Now let's have a look into the alloy with 21% niobium in a bit more detail. So here on the left, we see the diffraction patterns during heating from room temperature up to 700 degrees C. And so at a low temperature where the martensite exists, there's not a lot happening yet. We only see that the peaks of the martensite, they shift which is due to thermal expansion. I will say more about this later on. But then this is denoted as range temperature range 1 here. But then we have a temperature interval here labeled 2 in red, where something happens, yeah, and that is in fact the decomposition of the martensite towards the equilibrium alpha and beta phases. And so it is very interesting to look at this decomposition in detail and how that takes place, and then we see in fact that this is a very continuous process. So the lattice parameter of martensite really gradually, continuously evolves towards that of alpha phase, yeah, and that tells us that also the composition of this martensite continuously changes towards that of alpha. So it is not a sudden process, but it is a continuous process where the niobium is gradually expelled from the martensite into the beta phase, and in that way finally alpha phase is formed. Now here an example for the alloy containing 28.5 weight% niobium. So that is now with more niobium, and there we see different reactions during heating. So we have here again on the left diffraction patterns from 3 to 600 degrees C. So initially the sample is fully martensitic. Again, we see the thermal expansion of the martensite, and then we have a temperature range 2 that starts from about 350 degrees C, where we observe isothermal, well, some call it martensite, but it is an isothermal alpha double prime. Yeah, so in fact, what we observed here that was very exciting was that the initial martensite that is present, it transforms back to beta phase. At the same time, there's also omega precipitation, very strongly, in fact. And then at one point, we see isothermal alpha double prime appearing. That is indicated here with the red dots and diffraction patterns. So the intensities of these reflections are when you see that they are quite weak. Some of them are quite weak. The volume fraction is quite low, but still it is present. So we can still see them, yeah. And this gives us the hint, or explains us that also here the alpha phase, yeah, it doesn't form immediately from the beta phase, but the isothermal alpha double prime here is some sort of intermediate phase that forms in the course of alpha precipitation. Yeah? So the alpha double prime is in general an intermediate phase between beta and alpha. And also here, during heat treatments, we observe the formation of this orthorhombic phase. So it's not only during quenching, but also during heat treatments, we see that. Then coming to the thermal expansion of these materials. So as already mentioned, for low temperature intervals, we mainly see the expansion of the martensite without additional new phases. And it turns out that some of these alloys, it's the high niobium alloys, that they possess very high thermal expansion and also very anisotropic thermal expansion. And in fact, these values, so that the thermal expansion, for instance, here along the A lattice parameters. So we have 3 lattice parameters in the orthorhombic unicell, and we have A, B, and C. And it turns out that the thermal expansion along the A direction of the alloy containing 36 weight percent niobium, that is in fact the largest linear thermal expansion that was ever measured in any solid material to date. And that is very exciting, in fact, and we see that this behavior is dependent on the composition. So in low niobium alloys, the thermal expansion is less strong and also less anisotropic, and the more niobium we add, the stronger the reaction to temperature is, and also the more anisotropic it is. Yeah. So now the question is, of course, how can we use that potentially? So due to the anisotropy of the thermal expansion, so we have 2 of the lattice parameters expand. So the unit cell expands along C and along A when heated, but it contracts along B when heated. Yeah, and because of that, there is a line or an orientation where the thermal expansion is 0. So that is indicated here in the bottom right figure with the red line. So that's the unit cell, the orthorhombic unit cell, with the line of 0 thermal expansion. And then we have orientations where we see a contraction, and we have orientations where we see an expansion. This depends then on the composition, as indicated here on the bottom left. For instance, for 21 weight percent niobium and 36 weight percent niobium, so this line of 0 thermal expansion shifts. And well, to exploit this thermal expansion, we would ultimately have to be able to control the crystallographic texture. So different approaches could be to obtain single crystal-like textures. Then the thermal expansion behavior would be more or less like a single orthorhombic unit cell, where we have well-defined orientations that do not expand, others expand, and others expand and others contract during heating. Another way would be to start off with polycrystals and introduce a texture by deformation, for instance. And there we would need a 010 texture component of the martensite to, in fact, compensate the positive thermal expansion with the negative thermal expansion along the B-axis of the martensite. And the third, we will also have to be able to control the volume fraction, in fact. So it will be necessary to, to control how much martensite we have in the samples in case we have multiple phases. And that would be a way to compensate a positive thermal expansion of a matrix by martensite embedded in that matrix. But eventually, we will have to be able to control the crystallographic texture of the martensite, and that is the way forward to also control its thermal expansion. And we can think of various applications of such kind of materials, in thermal actuators and sensors, for instance, in satellite technology, space technology, car industry, and so forth. Yeah, with that, I'm at the end of my presentation. Thank you very much for your attention. That was all I wanted to show today. And if there are any questions, I'll be happy to discuss. Thank you.
Thank you, Dr. Matthews, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation.
Thank you. You're welcome.
Okay, so our next presenter is Dr. Rizjer Kapika from Łódź University of Technology, Poland. Hello,
Yes,
Dr.
hello.
Rizjer. Yeah, just a minute. I'm going to make you the presenter. Yes. Okay, you can share your screen with us.
Okay.
Yes, it's visible.
Okay, so once more, hello to everyone. I am Ryszard Kapita from...
Hello, can you please zoom in your screen, like we cannot able to see the poster properly?
Okay. Okay. Now you see it?
Yes, please try to more, like you can zoom in some more.
Because now is the full screen view and should be looks.
No, in full screen, it's not visible. Like we can able to see your poster, but not the content.
Okay.
Yeah, better you keep it like this.
So this is the the best what I can do.
Okay.
So I try to. Okay. Okay. So now after this 2 days of webinar, I know that poster presentation wasn't the best idea, but I try to shortly tell you about what we have done in our laboratory. So the presented poster is devoted to topic related to carbon dioxide conversion and utilization, and what we have done in laboratory. The first two, we prepared the series of iron-based, cobalt-based, and mixture of these two metals films. The second step was the characterization of this material using X-ray diffraction, XPS, and scanning electron microscopy. And the last step was the catalytical tests, which was performed in tubular reactor prepared from quartz. And I try to shortly show you and told you about what we have used and what we have done, what we have get from analysis. Firstly, we used plasma reactors, which are working at low pressure with radio frequency glow discharge. We used two monomers, cyclopentadienyl cobalt dicarbonyl as cobalt monomer and iron pentacarbonyl, where the cyclopentadienyl cobalt dicarbonyl was used with constant flow, and we changed the flow of iron pentacarbonyl. We used 60 watts as power discharge. The deposition time was 30 minutes, and after deposition, each sample was thermal treated in argon at 400 degrees centigrade for 30 minutes. At the beginning, we of course try to get composition of these samples. We use standard scanning electron microscopy with IDE-AX to analyze it, and we get that prepared samples are from cobalt base, where was only cobalt detected, to iron based with different molar ratio of iron and cobalt. You see on the graph how this composition changed. Of course, we to analysis used not directly composition, but relative content of iron and cobalt, just like you see on this graph. To analyze and characterize the nanocomposites, we used X-ray diffraction. We get that in cobalt-based catalyst thin films. We observed reflection from hematite, observed reflection from metallic iron, and from alumina. It's connected. This reflection comes from support which was used to deposition. Because we use Cantal steel, which was calcinated, and this is the reason why we have alumina on the surface of this Cantal steel. And for cobalt-based catalyst, we observe the peak which belongs to cobalt oxide on second stage of oxidity. And then, of course, we look only the sub. For iron-based, additionally, we see magnetic Fe3O4. However, we don't see cobalt, which was expected. X-ray photoelectron spectroscopy, of course, do not give us a pure answer for nanocomposite for iron and cobalt. This middle graph, because the bonds which are connected with cobalt and iron oxides are in the same place. So we analyze only cobalt-based films and iron-based films, and reached results confirms that the composition which was get from X-ray D-analysis. Then we proceed also the scanning electron microscopy. We prepare macro pictures for whole samples, and on the left you see that the pure support. It's the surface of calcinated Cantal steel, and you see the nanostructure which is observed on the surface. Then you see pure cobalt-based catalysts, and we observed and we analyzed it. This pictures and these photos, and when we state that this surface is exhibited the pattern that accurately reflects the morphology of the support, which is written on the poster. Then we observe iron-based catalysts, and we observe that the surface is large globulars with a finely folded surface. However, the composites are different. The structures are the structures are bigger and quite different from cobalt-based and iron-based catalysts. And the most important thing which we done in laboratory, it was catalytic tests, which was performed in quartz tubular quartz reactor. At what the catalytic set you see on the picture, and what we have done. So what we have get. We observed that cobalt-based catalysts, it's quite active and selective. However, the products which we observed was only methane. and the selectivity to methane reach at 400 degrees of centigrade almost 100%. Then we analyzed the iron-based catalysts, and we got that these catalysts are not so active because the conversion of carbon dioxide is only at level at maximum 10%. However, the selectivity, we observe only carbon monoxide, so selectivity is at 400 degrees of centigrade is close to 100%. However, the most important results we get for nanocomposites from iron and cobalt, when we expect that in products should be methane and carbon monoxide. However, even small addition of iron to the sample inhibit the production of methane. What we see on the graph, that selectivity goes to 100%. However, for carbon monoxide, and goes down to zero for methane, for 400 degrees of centigrade. However, the conversion of carbon dioxide was lower than for pure cobalt-based catalyst, and reached only 30% of conversion. And we expect that the mechanism will be just the similar for pure cobalt and iron based catalyst. However, this mechanism was different because we do not observe the methane, and just like you see the yield of carbon monoxide and methane, the predicted yield is much lower than this which was observed and analyzed for this reaction. So I think it will be everything from me. Thank you.
Thank you, Dr. Rizjan, for your presentation. Is anyone having any questions? Okay, no questions from anyone. Thank you once again for your presence and presentation.
Thank you.
Okay, our next presenter is Dr. Alexandra Kazirska from Łódź University of Technology, Poland.
Hello.
Hello, Dr. Alexandra.
Do you hear me well?
Yes, perfect. Now you are the presenter. Please share your screen with us.
Okay. Hopefully it will work.
Yes, definitely it will work. Yes, perfect.
Okay.
It's visible. Yes.
Great. I'm very happy because there were problems today a little bit sometimes. So I am, my name is Aleksandra Kędzierska-Sar. I'm from, as you say, from the Łódź University of Technology as previous speaker. So today I will tell in a few words about tungsten-containing thin films deposited with cold plasma and their catalytical activity. And motivation of my work was just to use the CO2 gas, which is not very friendly seen in our world now, to make reduction with hydrogen to syngas, which could be used for different reactions in chemistry. And for the deposition of these thin films, I used cold plasma system. which is shown in the figure here. As a precursor, I used tungsten hexacarbonyl, and the line needs to be heated up to 100 Celsius degrees. And the precursor entered the line through sublimation, and then all chamber was heated. Upper electrode and lower electrode, I used two different parameters, 25 Celsius degrees and 100 Celsius degrees, and also two different powers, for 40 watts and 80 watts. I obtained 4 different layers, and I deposited it on as Richard as well, on a calcinated Cantal steel. So here you can see the morphology of it. It's aluminium oxide, which is arise on the surface of Cantal steel during calcination process. And then when I obtained my thin films, I of course look on it on structure by XPS and also SEM with ADS, and I tested how they work in catalytic test in tubular catalytic reactor made from quartz tube, as you can see on the figure on the right. The samples were in the middle of the tubular reactor. It was Cantal mesh with deposited thin films, and I measured the signal of resulting results of the reaction. And the success was just to get as much as possible CO gas. So with gas chromatography, I did it. So the results of my work, first I will show you the structure of my thin films. As you can see, there were no big differences between different parameters, and by ADS, by energy dispersive X-ray spectroscopy, I measured the element content of these films, and there were also not a big difference between them. The chromium and iron and alumina origin from the Cantal steel, so the X goes deeper through the thin film. But XPS analysis, which is shown on figure C, D, and E, results of XPS analysis, it's analysis dedicated to thin films. As you can see, I just detect tungsten, oxygen, and carbon in different amounts. And thanks to XPS, it was also possible to analyze the element, the chemical composition. So I know that it's tungsten carbide on the surface, as well as tungsten oxide with different VO3 and VO2, and in different ratios. And catalytical activity, I measured each sample 3 times, so from 200 to almost 700 Celsius degrees. Then I cool it down in the flow, under flow of argon, and then re-examine it again. So the run 1, run 2, and run 3 catalytic tests. There were some slight differences between samples. So the higher conversion of CO2, so the biggest amount of obtained CO gas was for sample obtained with the lowest, as I can say, lowest parameters, so 40 watts and 25 Celsius degrees, but the stability wasn't so good. On the other hand, the green and red points, so two different samples, has a little bit smaller conversion rate, but they were highly stable. And to analyze why samples behave differently, I conduct also a post-catalysis examination with XPS, SEM, and also XRD measurements to determine what kind of changes came up on the surface during the catalysis. So as you can see on the figure G, there were changing the chemical composition during following tests. So generally the tungsten carbide amount increases slightly during tests, and the Wu6 plus amount is lower with following test for almost each sample, and Wu tungsten 4 plus is increasing. Only one sample was behave in opposite way, and this sample oxidize totally after run 3, was oxidized totally, almost totally after run 3, and this caused the deactivation of the sample. There were no differences big differences between morphology after tests, and also XRD measurements show that a slight amount of Wu tungsten carbide with pattern tungsten 2 carbon arise during the catalytic tests on the sample. So to conclude, it is possible to obtain carbon-containing thin films by cold plasma process, and it is possible to change the amount of different of chemical composition by changing the parameters of the method, and this chemical composition determined the catalytic behavior in CO2 conversion to synthesis gas. And I think in further work I will try to investigate also this thin films in other reactions like dry methane formation. Thank you for your attention, and I will be happy to answer your questions.
Thank you, Dr. Alexandra, for your presentation. Is anyone having any questions? No questions from anyone. Thank you once again for your presentation. Yes. So our next presenter is Elka Madhuka from Heroi University, United Kingdom. Hello, Dr. Elka. Are you ready with your presentation?
Yes. Hello.
Okay. So please share your screen with us. Yes, it's visible.
Yeah. Hello.
Yes, it's visible. Please
Yeah.
zoom in
It's
your
clear?
presentation. Please make it zoom in so that we can able to see this presentation properly.
Please, can you tell me where can I zoom it out
Yeah,
or zoom it
here
in?
in the right corner, like in the bottom of your screen, you can enlarge the at the right side corner, right side corner. Here in the right side corner, please increase the bar.
Right.
Bottom at the bottom of your screen.
At the bottom of my screen.
Yeah, at the bottom, at the right side of your screen, like the bottom, where you have the option to slideshow and everything.
Just a minute. I need to figure it out. At the bottom of my screen, there is no bar. There
Yeah,
is no.
here there are options. Yeah, please go move. Yes, after this option, yes, after that, then again, here there are plus and minus sign, right? 14% it is visible.
Sorry.
You can increase that one to 50%.
I think the scroll bar is getting covered by the meetings panel.
No, it will be not visible to us. It's only visible to you only. We will only we can able to see your screen itself. That's it.
I'm
Yeah,
so
here there
sorry. I'm
is, you
just
can
trying to.
see, yes, plus and minus sign is there, right? At the right side corner.
No, it is not there.
Yeah, after that option.
After that,
Beside,
there is the meeting screen is appearing. The
you can
okay, yeah,
please move, drag it to sideways.
yeah, I got it.
Yes,
I
yes,
got it.
yes, yes, yes,
Yeah,
perfect.
is
Yes,
it clear enough?
yes, it's clear.
Okay. Hello and good evening to all. My name is Alka, and once again, I talk about my ongoing PhD research work, which is concentrated on propelling sustainability in textile. And the medium of doing that is with the help of bioactive plant pigments. And what we are trying to achieve is the textiles that are colored with it and are also functional. Textile industry is actually second largest polluter in the world, and that propels my research towards green chemistry, sustainable chemistry, and the emphasis is on obtaining functional textiles that benefit human health, and the entire processing is ecological, and therefore it benefits the environment as well. If you remember, earlier I had cited two examples. Here I am citing another two examples on the similar lines where we are applying herbal biomaterials, namely neem and tulsi, holy basil as it is known as, for application on textile fibers and yarns. And we are further analyzing it on the ATR FTIR. Let's have a look at the processing part of it. Here is the pictorial depiction of how we process herbs, we obtain extract out of it, and we apply it onto the textile substrate. The significant green chemistry that is operating in the system is denoted here by the chemical structures that are predominant in the neem herb. One of the significant features here is that the principles of biochemistry are applied over here, where we are utilizing plain distilled water as solvent with no chemicals, additives involved in the processing. The entire processing is also conducted at the low temperature, room temperatures, and therefore ecological. Here I focus a bit on the analysis part, which is important for the research, as it helps us identify the significant functional groups that are inherently present in the plant pigments, plant phytochemicals, and that is what makes them bioactive and functional. Here we can see the ATR-FTIR done on the reflectance mode of both the herbs in their raw state, and this is when it comes onto the merino wool yarns. And as identified, it is very interesting to note this result that we have come up with, where the phytochemicals that are dense in the herb, like here I have cited the example of tulsi, they are getting transferred onto the merino wool yarns. And this is noted by the difference in the functional groups that were noted. And if you look at this side of the poster, I have mentioned the significant phytochemicals that are inherently present in these herbs. And these are the main chemicals that are operating when they are transferred onto the fiber fabrics. And the function has been antibacterial and antifungal. And further to the research, we perform these tests on the resultant fiber fabrics, which confirms the functionality of the textile substrate. Another significant aspect of the research is the ecological characterization of the processing, where we are hypothesizing, where we are processing, we are claiming that the process is ecological, the materials are renewable, and it will all propel sustainability in textile with the help of sustainable chemistry and green chemistry that is involved. This is the ecological characterization that supports the findings, which is reflected in the table 1. The values derived here are very interesting, where we noted that the original water ORP shifted from negative to positive values, which is a very positive sign. And it shows that the surplus solution, herbal solution that is left after processing the textile substrate, fiber, fabrics, and yarns of merino wool, bamboo, and banana, the surplus solution is reusable, biodegradable, and safe to be disposed in the aquatic water bodies without causing any problems to aquatic life or the life on land. I have signified here the processing with the neem herb and the analysis with the tulsi and neem herb that were the main that the processing was done with. But we had worked with 21 herbs, and each of them have given results on the similar lines, and this propels the sustainability in textiles. And the main components that are working out over here are the plant phytochemicals adhering to the ideologies of green chemistry. chemistry. I would finally like to mention the references, significant references, and the acknowledgement part, where I would like to thank Coalesce Research Group and Heriot-Watt University for giving me the opportunity to talk about my research topic. Thank you so much.
Thank you, Ms. Elka, for your presentation. It was a nice presentation.
Thank you.
Is anyone having any questions? Okay, no questions from anyone, I think. So thank you once again for your presence and presentation.
Thank you. Thank you so much.
Okay, so now we will move towards the video presentations. So I will be sharing my screen to play the video. Yes, I will be sharing my screen. Just a minute. Yes, is my screen is visible to everyone?
Yes.
Okay. So the next video presentation is from Dr. Jonathan Quinson from University of Copenhagen, Denmark. So I'm going to play the video first. Yes.
Hi everyone, and welcome to this presentation. I'm sorry I cannot make it.
Is the video is audible to everyone?
Hi everyone, and welcome to this presentation. I'm sorry I cannot make it in person to that conference, but I hope you will do the presentation anyway. So today I'll be talking about surfactant-free colloids. I'm trying to convince you that first, it's possible to make nanoparticles without using surfactant, and then you have many benefits of doing so. So this is a quick overview of the presentations. I will be talking a bit more specifically about precious metals, so I'll just give a quick introduction, and then we'll move on to colloidal synthesis, and more specifically surfactant-free colloidal synthesis. I'll be talking about precious metals. So precious metals are, for example, platinum, iridium, palladium, gold, silver, and they're used in many, many different types of applications. It's a huge business overall, worldwide, and I'm focusing more specifically on catalysis, but they can be used in many different other types of applications. The most common one where you may find these sort of elements like refinery, chemistry, the automotive sector is quite known. For example, the chemicals, the catalyst that makes your car less polluting are based on precious metals. And personally, I'm more focusing on electric catalysis and mainly fuel cells, which is aimed to derive electricity from gases, or electrolysis to split water and get clean hydrogen. But whichever way you look at it and whichever applications you may have in mind, what's important to keep in mind is that those precious metals are extremely rare metals. So they are not abundant, and therefore we need to use them, whichever they use it, we need to use them extremely efficiently. And the point of the presentation today is to argue that actually if you develop surfactant-free colloidal synthesis, you might be able to use the precious metals extremely efficiently. So I move now to the colloidal synthesis. And we believe that by doing colloidal synthesis, there can be an optimized use of the precious metals. The way you can think of colloids to optimize the use of precious metal is to develop nanoparticles. When you develop nanoparticles, you have a high surface to volume ratio, and therefore, especially if you think of catalysis, you optimize the use of the surface atoms. As in nanotechnology, what you want to be able to do is to control independently the composition and the size of the nanomaterials. In the case of catalysis, more specifically, we also want to be able to immobilize the nanoparticle on the support to do heterogeneous catalysis. And therefore, we want to be able to control the nature of the support as well as the loading and the distribution of the nanoparticle on that support. And typically, what the industry is doing is methods called incipient wetness, or impregnation calcination, where they will put the precursor on the support, reduce the precursor directly on the support, and get the nanoparticles. There are several drawbacks for this method. First, it's relatively challenging to control the loading. of your nanoparticles, because you will need to do the cycle several times to read the right loading. And by doing that, you have different sizes, which also means that you will know how to do that for a very, very specific substrate or support. It's very much support dependent. We have three drawbacks that maybe there is room to improve. So with Coalesce, you can on the one hand prepare the nanoparticle as a dispersion or a suspension, and on the other hand, take virtually any support. And when you mix the two, you technically are able to deposit nanoparticles with the same side in a controlled manner on virtually any support. And that has a lot of advantages. This slide may be a bit scary, but don't worry, I will explain what this is all about. This is just to stress that when you develop a catalyst or when you have specific applications in mind, there are usually many steps that goes all the way from the preparation of the catalyst down to the application. So I will just take an example, the one just above me over there, where once you prepare your nanoparticles, you may have washing steps before you get the supporting step, in which you have to maybe remove solvent, evaporate solvent. Then it comes to dispersing your supporting catalyst on a given solvent to prepare what in electrochemistry is called inks that would then just be dispersed. And the quality of this ink or the type of solvent you would use will depend on the nature of the support and the loading and the way you've been preparing your catalyst. Once you've got this film, which is the number 6 on the scheme, you can then go to testing, and then you have different type of testing depending on the amount of materials you have, the condition you want to test, and that can take quite a lot of time in testing before you actually reach a point where you develop a technology that is actually useful in real life application. So in order to address this very complex system, we've been developing what we call the toolbox to systematically study the effect of the different steps. And at the core of this toolbox are colloidal synthesis. Because once you control the synthesis of the metal, you can play with all the different parameters. Different washing, different supporting step, different loading, different distance of the nanoparticle on the support. And what I'm going to try to show you in the next slide is that actually we've been able to develop this toolbox thanks to surfactant-free synthesis. And I will give you examples of what we've been able to investigate a bit more thoroughly thanks to this approach. So first of all, maybe I should say that most of you may be familiar with colloidal synthesis, where typically you have a metal precursor, a reducing agent, a solvent, and very often you will hear that you need additives or polymer or stabilizing agent or even DNA to make sure that the nanoparticles do not agglomerate. This is very common to see that in the literature. However, this is not true for all systems. It's been known for quite a long time now, from the year 2000, that you can synthesize especially precious metal without the need of any surfactant. And these syntheses are extremely powerful, and they work for many different systems. They work in solvent like ethylene glycol. More recently, it's been also shown to be possible to do this sort of synthesis in glycerol, and probably many other polyols. And if you look at more physical methods, there is also the laser ablation, where you shine a laser on a piece of metal to get nanoparticles with the same composition as this metal. So there are around quite a few different approaches to develop surfactant-free synthesis. So what's the benefit of going for surfactant-free synthesis? As you can see here, in the typical scheme of a synthesis that uses surfactant, you list the surfactant and the precursor, things start reacting, and you may not necessarily understand very well how and when the surfactant comes into play. In the end, you have a nanoparticle with surfactant, and that's where the problem comes. Because in many cases, for the next step, for the applications of the nanoparticle, you need to maybe functionalize the nanoparticle, which typically means removing the surfactant you have, because there may not be the one functionalized nanoparticle you want. And this surfactant removal can be extremely challenging. And usually it's not completely removing all the surfactant. There are other considerations in the challenge of using surfactant, which is that surfactant are typically toxic and derived from fossil fuels. The removal, as I just said, is very challenging. And adding more chemicals to the synthesis potentially add more impurities, which can lead to problems regarding the reproducibility. In light of these, you can easily see that a surfactant-free synthesis is much better because you have less doubt on the role of the surfactant and how much surfactant you need in the first place to get nanoparticles that are much more easily functionalized, which means that you can also more easily use them as building blocks for other nanomaterials, or you can easily deposit them on support without having to remove any of the surfactant. So now we move to the polyol synthesis and give you an example of what we've been achieving with this synthesis, especially regarding electrocatalysis. So we've been working a lot with the ethylene glycol synthesis, which has the convenience to be very easily induced by different ways in oil bath, using UV vis, or even microwaves. And more recently, we've been showing that by controlling the NaOH to metal ratio, we can control the size quite efficiently. And that was quite a breakthrough because that allows us to do very interesting fundamental studies. So here I give you some examples of what we've been achieving. So first, we produce a catalyst with a colloidal approach I just explained that has the same size of nanoparticle and the same loading as a conventional catalyst. And what you can see is that the mass activity in blue that we've got here is much higher than the equivalent that is a commercial catalyst. And that was possible to be achieved precisely because we understood and we controlled every single step in the preparation of the catalyst. And this opened a whole range of new opportunities for study. And in the most recent work, we've been showing that you can actually very finely tune the activity by controlling not only the size, but also the loading of the support, but also how much distant from each other the nanoparticles are. And quite interestingly, we show that if you manage to get the nanoparticle very close to each other, without agglomerating, you have a huge increase in the mass activity. And that's very positive because that's a reason to go for high loading. And in electrochemistry, high loading can be something like 60 to 70 weight% of metal on support, the support typically being carbon. And that's interesting because in many cases, people want to go to such high loading to ensure the stability of the catalyst over time. But this study showed that actually by doing it carefully in a controlled way, you can actually gain a lot of mass activity by something we call the proximity effect, which relates to the interaction of the nanoparticle when they get close enough to each other. And that's a very positive synergistic effect that you have by designing carefully the nanoparticles being small and very close to each other. That also means that we're now investigating many more questions on the dissolution behavior and the stability of this catalyst. And here again, there is a benefit to go for relatively high loading and very relatively small size, despite the fact that the small size are typically less stable. Furthermore, once we've been a bit more aware of this proximity effect, we've been looking at what happens when you do nanocomposites. And by that, I mean mixing different types of nanoparticles. So in the first example on the left, we've been mixing platinum nanoparticles and iridium nanoparticles, and we've been comparing with an alloy, so a mixture of platinum and iridium within the same nanoparticle. And what we observed is that in this mixture, we decrease the activity for the oxygen reduction reaction, which makes sense because the oxygen reduction reaction is very well performed on platinum, but not iridium. So if you add iridium, you lose a bit of activity on the oxygen reduction reaction. And that makes complete sense. But quite interestingly, for both the mixture of platinum and iridium and the alloy, there was an increase in the OER activity, which is the oxygen evolution reaction. And that's expected as well because we know that iridium is a good catalyst for the oxygen evolution reaction. But what was even more interesting in that study is that when you have a mix of platinum and iridium, you had a higher stability than using just platinum or just the alloy. So following up on this idea of having not alloys or not different elements within the same nanoparticle, but having different nanoparticles sitting next to nanoparticles of a different composition, we started to investigate different combos of precious metals, still using surfactant-free nanoparticles and the general recipe and toolbox approach I mentioned. And in the most recent example, we've been looking at the difference of adding iridium to platinum, because as I just told you, we saw a positive effect of mixing platinum and iridium nanoparticles. So we compared it to the case where we had gold and platinum nanoparticles, and we saw that this mixture of platinum and gold showed increased activity and stability compared to the platinum only. So another interesting way to play around with the surfactant-free synthesis and nanoparticle resulting from the synthesis to be building blocks for more fundamental studies. Having said that, there is one question to address: is how this knowledge that we gain from fundamental studies can be transformed to more realistic applications. So in order to bridge the gap between academia and industry, we need to focus a bit on how easy it is to make this fundamental knowledge available to industry. And that means addressing the production of the nanoparticles, the processing of the nanoparticles, and their performance. And I'm going to touch upon that now in the rest of the talk. So what we know well is that the polyol synthesis is definitely a surfactant-free synthesis that leads to very active nanoparticles. Take ethylene glycol, a base, and a metal precursor, and you can easily get the nanoparticles. The problem here is that you need several washing to collect the nanoparticles, and therefore you generate waste because ethylene glycol is a relatively viscous solvent with a high volume. So what we wondered is that can we just switch the polyol for a monoalcohol? And we did so, and quite surprisingly, it works very well. We were very surprised to find that out, and we were not the only one. During the reviewing process, some people actually rated that it was actually surprising that no one managed to do that before. Maybe we were lucky to hit the right window to start with, but it's completely possible to develop stable colloidal nanoparticles with that surfactant just using monoalcohol. So therefore, quite naturally, we developed different synthesis, and we showed that we can use it very easily for bimetallic nanoparticles. We can use water or oil-based synthesis as well as UV-based synthesis or microwave synthesis to initiate the synthesis and the formation of the nanoparticle. The size control can easily be achieved by adding water. It's a very, very simple synthesis that really gives you active nanoparticles in the sense that these nanoparticles are surfactant. So here I'm giving you an example of how active these nanoparticles are. So here we're talking about iridium nanoparticles, and in blue you will see the properties for the oxygen evolution reaction. So it's an electrocatalytic reaction of the nanoparticle produced by our method that we call COFOCAT, which stands for Coalesce Catalysis, and it's patented now. And you will see that we have a factor 3 to 10 more mass activity compared to other iridium nanoparticles reported in the literature. And that comes from the fact that we do not use surfactant. We can easily remove the solvent to immobilize the nanoparticle, and therefore we get such a high activity and a much better use of the nanoparticle with a process that is more green and more sustainable in the first place. Due to the high activity of these iridium nanoparticles, we were also able to study the effect of different subtle parameters in the preparation of the nanoparticles, as well as their activation by electrochemical treatment. So this is just a slide to illustrate to you why, by suddenly having so active nanoparticle, we can actually design more studies to understand how important some parameters are or not in the preparation of the nanoparticle. And most recently, we've been actually comparing the effect of using different solvents, so the ethylene glycol, or methanol, or ethanol in the preparation of this nanoparticle. And what we observed is that the nanoparticles prepared in ethanol were more active, not because they were interestingly more active, but because it was much easier to deposit them on the support, in that case carbon, and therefore that was highlighting the importance of thinking of your synthesis together with what the next step after the synthesis will be in order to optimize the use of the nanoparticles. And we're also starting to see some proximity effect, just like I explained to you before with the ethylene glycol synthesis. We see this effect also with that synthesis in monoalcohol. Following up more practical examples, here you have different catalysts from an industrial partner, where you have platinum on alumina at different loading. And what you can see is that the size of the nanoparticle is relatively broad, and they tend to agglomerate, especially when going to higher loading. The nanoparticle agglomerate, which is typically a problem when you've got in-situ wetness techniques to prepare the colloids. And what we did is we take exactly the same support, but we prepare the samples in our approach with colloidal synthesis. And what you see is that, in contrast, in our case, we have very small nanoparticles, very narrow size distribution, regardless of the loading. And as you can expect, at the nanoscale, this will have an impact on the catalytic properties. So this slide is a bit heavy, but I'm gonna go through it with you. What you can see on the graph is the time needed to perform the full conversion of 2-butanol to 2-butanol, and that's performed by the catalyst we just saw. So I'm gonna start with the black line, which are the industrial catalysts. What you see with the industrial catalyst is that when you increase the loading, you actually see that it takes longer time to achieve the full conversion. This is not quite clear because you have more metal, so potentially more catalyst. But you need to remember that when you increase the metal loading, actually you lose the nano feature because the nanoparticles start to agglomerate. Therefore, you need more time to achieve the conversion. In contrast, with the catalyst we prepare, you can see first that for the lowest loading, the 1-way%, the catalyst we prepared by our method is much more active in the sense that it's much faster to reach the full conversion compared to the same catalyst with the same loading prepared by the industrial part. And more interestingly, maybe, when we increase the loading, we do see that we are much faster to reach the full conversion, which means that this despite going to a higher loading, we don't lose any activity. All the catalyst that we put in is more active, and that's why we can achieve faster conversion. And that means that in terms of mass activity, turnovers, and recyclability, the catalyst prepared by this colloidal approach without surfactant is much easier. And at the end of the day, that means simple process and production method of the catalyst. And we can, for example, show that we could recycle the solvent, so that's also diminishing the cost in producing the catalyst. We have overall a more efficient use of the precious metal, and that means that technically we need less material to achieve the same output, which means that in terms of reactor design, you may need less material to still get the same output. So overall, whichever way you look at it, this approach can save a lot of money at the industrial scale. This example is just to illustrate further to you that the catalyst is competitive in terms of mass-related activities compared to the benchmark. And also we have a competitive recyclability of reusing the catalyst several times. I will now move to the last part, which is a bit more fundamental, but also quite interesting, and where surfactant-free synthesis can actually bring a lot of answers. And that's more based on the synthesis itself and the mechanism of synthesis. Because obviously you may wonder how these nanoparticles stabilize, despite the fact that they don't have any surfactant. So the synthesis of nanoparticles, in this case, platinum nanoparticle, is still subject to debate. There is a general consensus that nanoparticles are formed from precursors that get reduced and then the nanoparticle grow, but not necessarily a very clear understanding of how that works, and especially not a clear understanding of what the role of surfactant. So to start addressing this question, we've been looking at synthesis without any surfactant, and especially using a technique called PDF, we've shown that in the case of the synthesis without surfactant, we actually form very complex structure, which looks a bit like a network of prearranged platinum atoms in a network of platinum and chloride atoms that formed before the nanoparticle actually formed. And we could argue that maybe this prearranged structure with a relatively long range order may explain why the formation of nanoparticles is often referred to as a burst formation, which is a sudden formation of the nanoparticle from the precursor. And that may be possible because there is this prearrangement that we observe. Maybe more fundamentally, we also looked at the effect of solvent in the mechanism of both of the nanoparticles. And one key finding was that in the case of platinum, we certainly have contribution of negatively charged surfaces in the stabilization of the nanoparticle, but also the formation of CO itself on the surface. And this CO was especially clear in methanol, because it's more easy to oxidize methanol to CO and cover and protect the surface of the nanoparticle. We also observed a very strong effect of the cation in the stabilization of this nanoparticle, with the stabilization decreasing as the cation interacts in a more weak way with water. So a very complex system, or simple, depending how you look at it, simple compared to surfactant, but complex in the very subtle effect that can influence the stability of this nanoparticle. Having looked at the mechanism in a general way, we actually wondered if this knowledge could help us to develop even simpler synthesis. And we've been thinking a lot about which precursor to use to start with. And what we observed is that by leaving some of the precursor solution on the bench, they age and they change color, and X-ray absorption spectroscopy confirmed that we convert the platinum-4 to platinum-2 without forming the nanoparticles. And interestingly, as soon as we add a bit of sodium hydroxide to this solution of precursor, we actually get in 2 seconds up to minutes at room temperature the synthesis of stable colloidal nanoparticles. So once we thought that we explored a whole range of surfactant-free synthesis, we actually found that we can do things even more green, not only removing surfactant, not only having low boiling point solvent, which facilitates the processing, but actually doing the synthesis at room temperature. With this in mind, we also investigated other metals such as palladium, and again, the fact that we use surfactant-free synthesis lead to catalysts that are more active than the commercial counterpart, and also enables us to start investigating effects like what's happening during the electrochemical treatment. You can see on the TEM image at the bottom the catalyst before electrochemical treatment and after, and we can start understanding how the loss of activity is related to the change of size of the palladium nanoparticle. And in that case, it's a very simple synthesis that also happens at room temperature and give you 2 to 3 nanometer palladium nanoparticle, very well dispersed on the support by just mixing the reactants and let it happen at room temperature. So today in this talk, I've been talking about surfactant-free colloids in low boiling point solvents with a technology called CoFOCAP that we developed and patented. And I hope I managed to convince you that you don't necessarily need to go to a high boiling point solvent or high temperature to develop first nanoparticles. But on top of that, these nanoparticles are surfactant-free, which leads to a whole range of interesting properties. To produce the nanoparticle, to process them further, and that results in optimized performances. In terms of understanding of how this nanoparticle with that surfactant is stabilized, we now understand that there is an interaction between the solvent and maybe CO species on the surface. A key role of the cation that you may not expect, but that is clear when you start looking at surfactant-free synthesis, and also that we can now develop more temperature synthesis to make the synthesis even more. And the take-home message of this presentation that you may want to think twice of surfactant-free synthesis as a building block for your own research. I'm going to thank now all the people that have been involved in the different projects. It's quite a lot of people. I will thank especially Professor Matthias Arndt from the University of Bern, with whom we've been collaborating a lot, and the former postdoc from this group, and also the funding from the Marie Curie fellowships that have been awarded. And once again, I'm really sorry I can't be here in person, but if you have any ideas, any suggestions, any questions, please do feel free to keep in touch. Drop me a mail. I'm relatively free and very happy to discuss with you further if you have ideas or collaboration or suggestions. So I'm looking forward to hearing from you. Thank you very much.
Thank you all for listening to the video presentation of Dr. Jonathan Quinson. We have another video presentation from Dr. Monica Parletto from University of Catania, Italy. Now I'm going to play the video presentation of Dr. Monica.
Good morning, I'm Monica Parlato from University of Catania. The title of this work is Greenhouse Covering Plastic Films Waste Management, a case study GIS-based model. Our economy framework, the conversion of waste to new raw materials is an important aspect of increasing resource efficiency by reducing environmental pollution and CO2 emissions. One of the biggest environmental concerns is plastic pollution because of the long-life material. That plastic can take hundreds or thousands per year to be decomposed. And because more than 85% of plastic waste ends up in landfills or are wrongly disposed of. Circular economy involves eco-design, waste prevention, recycling, and energy efficiency. The direct consequence is that the maximum quantity of resource will be restored by decreasing landfilled waste amount. Moreover, this transition from a linear economy to a circular one could be implemented by reducing plastic consumption. In Europe, plastic material, especially plastic films used in agricultural activities, are more than 1 million tons per year. In the absence of a correct policy disposal of plastic films, the environmental degradation takes place with serious consequences for air, water, and landfill. In 2011, the agricultural plastic waste APW recovery rate in Europe was around 46%, and the mechanical recycling rate was about the 23%. From the recycled process could be obtained a new plastic raw material, such as plastic granules. APW recycling could reduce pollution, CO2 emission, and prevent economical loss and environmental impacts due to the development of greenhouse systems. But often the cost for correct APW recycling process could be higher than the cost of making plastic from virgin material, especially if we consider the collection, transportation, and cleaning costs. The waste considered in this study are plastic films used for covering greenhouses. Okay, the plastic films used starting from the 1950s as covering material for greenhouse. This system was developed quickly and it is still in continuous growth. In fact, yearly, the world agricultural plastics consumption amounts to 6.5 million tons, of which more than 350 tons only in Italy. The use of plastic films are some positive effects, of course, but also some negative effects. The positive effects are concerning the shortening of the growing period, the defense of crops from environmental risk, such as bad weather conditions, birds, and parasites, and create the creation of microclimate favorable to plant growth. On the other hand, the negative effects are the increased diffusion of protected crops that generate a large amount of agricultural plastic waste that require a properly collection, disposal, and recycling process. Among the different types of agricultural plastic waste collected and directed for recycling, a huge amount is constituted by plastic films used to cover greenhouses, mainly represented by low-density polyethylene, ethylene vinyl acetate, polypropylene, or polyethylene. The solution could be a correct disposal, management, and recycling process of plastic. For this reason, the aim of this project is the need to reuse agricultural waste for producing sustainable materials. Since the sustainable reuse of agricultural waste depends on their availability and geographical location, a methodology was put forward in order to locate and quantify the wastes considered in this research study, the plastic films that are used for protected crops. So, the geographical location, the availability to develop a sustainable reuse. In this study, a GIS-based method was carried out to locate and quantify the yearly amount of agricultural plastic waste coming from covering crop shelter. This method was applied for validation in a study area located in South Italy. The geographical area chosen to validate the methodology is the province of Ragusa. In fact, the province of Ragusa is the highest, in the province of Ragusa, we have the highest concentration of greenhouse in Italy. The aim is to improve a correct management, recycle, and reuse process of plastic covering film in order to reduce environmental methodology. First, the first step was the case study individuation. After plastic waste index found in the future was adapted to validate the methodology. The second step was about the implementation of a geographical information system-based model for the agricultural plastic waste computation. At the end, the third step was about the quantification and location of the yearly plastic waste film. in the chosen area. First step, case study individuation. This study was carried out in province of Ragusa, in the whole province of Ragusa, South Italy. This province had the highest incidence of greenhouse with almost the 58% of protected crops. The area with the highest density of crop shelter were mapped. Then a suitable index to determine agricultural plastic waste amount was computed and applied to obtain heat maps related to covering plastic. With the aim of estimating the quantity of plastic films for the whole province of Ragusa, areas of about 150 hectares were selected within the territorial boundary. This in order to compute the related quantity of plastic films. Within each sample, crop shelter were subdivided into two typologies: tunnel greenhouse or A greenhouses. This slide, you can see the sample area location. In red, there is the boundary of the province of Ragusa. In violet or purple, the individuation of the first area, sample area. Individuation and location, of course. By tunnel greenhouse or greenhouse. This difference was deeply analyzed because for the same covered area, the coverage of tunnel type shelter needs a greater quantity of plastic films. If we compare the same area covered by a greenhouse style. This difference is due to the higher tunnel shelter slope, of course. As we said before, from literature, plastic waste index was chosen and adapted to this case study. In order to compute and apply on a GIS map to carry out our analysis of protected crop concentration. The equation chosen is PWI, so the plastic waste index, equal to SSCR for row, for TT, for life to 1, for UT. The result is a plastic waste index in terms of production of kilo production per hectare per year. In this equation, SCR is the surface correction factor. For tunnel greenhouse, it was 1.5, and for a greenhouse, 1.12. Row density. Rho was the plastic density that ranged between 920 or 930 kilo to metro. TK is about the plastic thickness, 180 micron or 200 micron. The life is the plastic useful lifetime considered ranged between 12 or 24 months, and at last the UCBC, that is the unit conversion factor. That this case was 0.12 cubic meters micron to minus 1 per month here and after. In fact, the computation of this index was modified by changing these parameters such as S, R, rho, T, and life. This in relation to different types of both protected crops and cover. After the GIS-based model was implemented for the APW computation. The GIS-based model was implemented by using data collected from base and thematic maps, as well as from digital color of the photos and farmer interview. To be more specific, the following dataset was used. So, we used the regional technical map obtained from an aerial flight performed on 2008, some digital color orthophoto at the scale of 1 to 10,000 obtained from an aerial flight performed in 2008, and reference system used was the Monte Mario Italy Zone 2 with a pixel ground resolution of 50 centimeters, and satellite color image from Google Earth database, which allow the recognition of synthetic crops in imagery dated 2017, which is the last available coverage. This image dataset was used in order to analyze the development of the greenhouse coverage system in the last 10-year time frame. And at last, of course, with the model was implemented by using also telephone farmer interview. The first step was about the quantification and location of the purely plastic waste field production. To compute agricultural plastic waste deriving from the plastic covering films, the following steps were performed. Firstly, a random selection within the province of Ragusa of the 30 area sample in order to cover about the 30% of the whole area covered by protected crops, divided in shade greenhouses and tunnel greenhouses. After detection of further polygon extraction of protected crops located in each sample, subdivided into two typologies, shaded greenhouses or tunnel greenhouses. After the GIS database implementation and the computation of the plastic film waste index. Basic statistic evaluation to compute the yearly amount of plastic film waste and production of thematic maps by GIS. So the areas with the highest density of crop shelter were mapped, then a suitable index to determine agricultural plastic waste amount was used in order to compute this quantity and applied to obtain heat maps related to covering plastic film. In this slide, have some preliminary results related to plastic film index. In fact, by changing the thickness of plastic films, by changing the two types of greenhouses, tunnel or a shaded, and by considering a life duration of plastic film of 12 months or 24 months, we estimate this value, this 8 value, and the average was the yearly, agricultural plastic waste average index was 1.7 tons per hectare by considering both the type of greenhouse. In fact, this average value is about the greenhouse system and the tunnel greenhouse system. The greenhouse plastic waste index mean value was 1.4 1,400 kilo per hectare per year, and the tunnel greenhouse plastic waste index mean value was about 1,900 kilo per hectare per year. Result. By analyze this result, see a series of heat map with a different level of concentration of pathetic crops was created. On the left, we see the heat map of pathetic crops in the study area for the whole province of Ragusa, with a different range of color starting from 0% to the maximum value that was the 8% of concentration of this greenhouse system. As you can see, on the left, the major concentration is on the municipality of Acate, Victoria, Santa Croce di Camerina, and a little part of the coastal area of Ragusa. On the right, we have the yearly amount of agricultural plastic waste on the province base of the whole province of Ragusa, divided for municipalities. Also, in this case, the municipalities the most compromised are Acate and Victoria, with the higher quantity of agricultural plastic waste for here. In fact, in these two municipalities, we have value ranging between 40,081 to 7,000 ranging from 481,782 to 712,265. So in conclusion, we can affirm that through the GIS model proposed in the study, it was possible to compute the agricultural plastic waste deriving from greenhouses cultivation system in the whole province of Ragusa, which was chosen for its relevance with regard to development of protected cultivation. The obtained result concerning the amount and location of agricultural plastic waste are essential for a better management of collection center, taking into account that the only existing infrastructure in order to optimize the collection process and reduce CO2 emission is the major responsible for the global warming. Was observing during the study that only one collection and recycle center is present in this area. Moreover, in view of obtaining new material from agricultural plastic waste and in order to reduce the transport cost of transferring agricultural plastic waste to the recycling plants, the optimization of the location of new collection center is required. GIS-based model results could provide the basic information for the analysis of the environmental impact to agricultural plastic waste. Therefore, this result could offer a suitable tool to improve the correct disposal management of covering plastic films and the related recycle points. Further consideration as about the location of the highest concentration of protected crops. In fact, almost all samples were located close to the coast because in this area was found the highest concentration of greenhouses. Territorial analysis showed that the major part of protected crops are located in the coastal area. So, despite despite the indication of the territorial plan of coordination of the Ragusa province. In fact, this territorial plan foresees the reorganization of the whole coastal area, especially about the use of the geographical area. This with the aim of reducing the anthropic load in the coastal system. We can affirm after this study that the indication of this plan, this territorial plan, was completely disregarded. Serious consequence for the geographical coast, but also for tourist activity. Thank you for your time, attention.
Thank you for listening to the video presentation of Dr. Monica. So if you're having any questions regarding the two video presentation, so you can mail to the concerned program manager. Yeah. Okay, so by this we came to end of our day 2 webinar, and I would like to thank all the attendees and participants of today's webinar. Hope you enjoyed this and gained some knowledge from the sessions, and we'll be glad if you could join us in our next webinar, which will be scheduled and the dates will be informed to you by mail, and we'll be very happy if you could share your opinion or feedback with us. Thank you.